Okay, so we try to be abnormally on time for Italians. So thank you. I wish to thank all the participants who are connected in this moment and those who will connect later. And of course, I wish especially to thank our speakers. The first speaker today is Joseph Teichmann from the Polytechnical School in Zurich. And then in the afternoon, we have Krista Cuchiero from Wien. Tomorrow morning, Lyudmila Grigorieva from Constance. And in the afternoon, Juan Pablo Ortega from San Gallo. The school today, this school, we wanted to make it, we went to the wonderful School of Financial Mathematics in Vienna, which was a joint virtual and physical school, and we tried to imitate, but unfortunately the circumstances couldn't allow it. So I mean, we have to do all this virtually. We hope to correct this, as everybody hopes, I think, as soon as we can. But nevertheless, this adaptation is what makes our species winning. So we have to do this. And let me just acknowledge the support by our funding contributors. So the Unicredit Bank, the Department of Excellence of Science of the Scuola Normale Superiore, and the European project So Big Data++. And finally, let me say that nothing would have been possible without the efforts made by the two organizers, who are Giulia Livieri and Piero Mazzarisi. So I really wish to thank them wholeheartedly, because they did a great job, and as always, it's easy to organize things when everybody else does all the dirty job, and this is what they have been doing. So really, thanks a lot, Piero and Giulia, for all your efforts. Okay, and now I'm really, really happy to introduce Joseph, and please go ahead. Thank you.
Thank you, Stefano, for the kind words in the introduction. Thanks, Giulia and Piero, for organizing the school so well, and Giulia for the beautiful webpage. We were optimistic up to the last moment that we could do it as a physical school. Then we switched at a certain point to the vision that it could be a hybrid school, and finally we ended up with a fully online virtual school. This is one of the messages of 2020, that predictions are not easy, in particular when it is about the future. I think 2020 is the year which proved my usual optimism to be, in many cases, the wrong indicator, what is going to happen in the future. Still, even though it is a virtual school now, we try to keep up the spirit and to continue following our research directions. And it is my pleasure and honor to start this school with a lecture which I named Randomized Signatures and Applications to Learning of Stochastic Dynamics and Portfolio Selection. It is a lecture Russian style. This means 2.5 hours, no break, and therefore also a challenge from the point of view of focusing. If a compact minority feels that the break is something you would like to see, just start. I personally do not have problems to talk for a long time, and but I will ask from time to time how you feel about making a little break. Concerning questions, I see that the audience is not really small due to the the great advertisement Julia and Piero did for the school. And therefore, it is most likely not optimal if you ask directly in the lecture, but usual easily working workaround is just to write in the chat, and Julia gives me a sign that there's a question, and I'm very happy to answer it. I also like questions in this virtual mode because it gives me the feeling that I'm not talking for myself, sitting in my kitchen for 2.5 hours. Just one question, Julia, that is okay for you to give me from time to time?
Yes, perfect.
Questions if there are questions in the chat, right?
Yes.
Okay, very good. So then I shall start, and I just start by reminding the abstract which I sent with this lecture. So we are learning in this lecture what signature processes are, and how to construct randomized signature processes, and how to relate this to the paradigm of reservoir computing. And you see here, I somehow cut off a part of the abstract, but I am not looking now why that happened. So the goal is to make you acquainted with signature processes, or signature as it is called in the theory of rough paths, and to relate this on the one hand to reservoir computing, which is a paradigm of machine learning, and on the other hand to construct randomized versions of signature which have almost the same properties as signature itself and fit even better into this paradigm of reservoir computing. And there will also be some applications to mathematical finance which might be of interest. What is very interesting about this lecture is, even though it touches very applied fields of modern mathematics, so this is approximation theory of dynamical systems and machine learning with a lot of concrete and beautiful applications, it also uses relatively abstract mathematics, which you find usually referenced in books of the Bourbaki group. So we will see that the connection between, on the one hand, abstract algebra and very concrete applications in machine learning is actually not artificial, but somehow natural. And we shall also see a couple of beautiful statements from functional analysis, which will be needed in order to do the proofs of our statement. And this is also a field of machine learning which is not only governed by empirical evidence that things work, which is very often in machine learning so far the case that we know empirically that certain algorithms work, even though we do not have a precise convergence proof. In the field of reservoir computing, and you just have to go to the web pages of Ludmila Grigorieva and Juan Pablo Ortega, who are also speaking here at the school, this is also provable machine learning. So we know about algorithms where we can prove that with certain levels of accuracy, approximations are possible. So in that sense, it's also from a mathematical point of view, a very satisfying field of machine learning. Of course, there are also other fields of machine learning where you have provable statements, but I want to point out that in reservoir computing, in particular due to the work of Juan Pablo and Ludmila, this is very much the case. So let me just give a little introduction what I'm going to speak about today. So first I would like to present, after some setting statements, the paradigm of reservoir computing. I will connect it to recurrent neural networks and signature representations. I will introduce a new aspect in signature, therefore I talk of signatures in the plural, the semi-martingale approach to signature representations. to make it also interesting for people who already heard this talk several times. So there's a new part of it, which is a very recent research result. And then we apply random projection techniques to construct reservoirs, and reservoirs actually in the very meaning of the word, and to prove some generalization results. And I have to mention with gratitude all the co-workers in this work. So there is Erdinç Akil-Dirim from my working group at ETH Zurich, and Xiang Su. They are both working on portfolio selection by randomized signature methods. And our joint work with Christa Cuchiero from Vienna University, who is going to speak in the afternoon, Lukas Gronon from Ludwig Maximilians University in Munich, Ludmila Grigorieva from the University of Constance, and Juan Pablo Ortega from St. Gallen University. And we are working on this theory of randomized signature in a discrete and in a continuous time setting. And to be more precise, what is also the theme today in my lecture is I'm going to speak about continuous time forward dynamical systems where we try to find reservoir type approximations. Good. As a first concept which I would like to introduce appears the concept of a controlled ordinary differential equation. A controlled ordinary differential equation is abbreviated by the word code, and this appears from time to time in the lecture. A controlled ordinary differential equation comes with a state space E, which can be a manifold of finite or infinite dimension. And the only thing you need to have for this object is a differentiable structure, such that you can talk about curves into this object, and first derivatives of curves and tangent directions. And as soon as you can speak of tangent directions, you can also speak of vector fields. And the vector fields are always denoted here by capital letters VI, and these are tangent objects. So think of Rn, then a vector field is just a map from Rn to Rn. Think of a manifold, a submanifold of Rn, then a vector field is a map from points of the submanifolds to vectors which are tangent, of course with usual smoothness assumptions depending on the very structure of differentiable structure of the state space of this manifold. And we are considering differential equations of the form that the first derivative of the solution y at the point t is a linear combination of vector fields vi at the point yt, so this is usual, but the linear combination is coming with weights which are, or with coefficients which are derivatives of another given curve. And this other given curve is usually referred here as control. And it's a curve which we shall always assume at least C1, such that we can talk about first derivatives. And this is exogenously given for this differential equation. So you imagine here as a curve from the real numbers, time to Rd, if we are given d vector fields vi, and given u, I can calculate at any point in time the coefficients of the linear combination of the vector fields vi, which are also exogenously given, in order to determine the speed at the point y of this dynamics. From the point of view of differential equations, this is a non-autonomous dynamics, and I usually will write the solution of this equation not only with the letter y, I will also write it from time to time with the notion evolution. An evolution just is the solution starting at the point S, can be 0, can be any other point, going forward in time and going up to time t and starting at a certain initial value at S. And the initial value is here denoted by little y, an element of the state space. And of course, there are certain conditions which have to be satisfied such that you have a solution. Usually, these are global Lipschitz conditions, but this depends on the geometry of the state space, how to formulate that. This is all done in classical geometry analysis, dynamical systems, and my chairman, Stefano, could give in many different areas of applications examples how such conditions look like, such that you have global existence of those equations. U is referred as the control. Vi are the vector fields. The solution is often, since it is a non-autonomous system, written here as an evolution. And we have actually several maps which we can consider. We could consider the map from the initial value y to the solution at time t. This would be the evolution map, or sometimes loosely speaking, even though it is not a flow, the so-called flow map. It just tells you how this dynamical system is transporting the point y within time t to the point yt. And this is usually under standard assumptions a diffeomorphism, or at least a homeomorphism, and one can try a lot of analysis in dynamical system is trying to understand better this homeomorphism. And I just want to make a very direct connection to machine learning here. When you think that you place yourself on Rn, so E would then be Rn as the input space, and you consider Yt then also an element of Rn, and in this case, let's call it the output space, and you imagine that you discretize your dynamical system with a standard Euler scheme discretization, and you imagine additionally that the vector fields Vi are actually neural networks. So neural networks are compositions of one type of nonlinearity, which is component-wise applied to the output of an affine function. So the affine function goes from Rn to Rn. This is our state space. And then I take the output and apply on this output nonlinearity. On every component of this n-dimensional vector, I apply one and the same nonlinear function from R1 to R1, for instance, tangent hyperbolicus, if you want. And some function which is interpolating smoothly between two values and is otherwise bounded. This would be called a shallow neural network. And if you take the discretization, the Euler discretization of this equation, then you have Euler discretization, let's say, with m steps. And when you think now about what the Euler discretization does, it is nothing else than concatenating affine function nonlinearity, affine function nonlinearity with some identity added, but actually it is in principle doing such operations recursively. And if you think about this procedure in detail, you actually see a deep neural network appearing. A deep neural network is a network where you repeat iteratively the procedure of having an affine function, this nonlinearity. And we took this as a model we took therefore these controlled ordinary differential equations as a model for feed-forward neural networks actually, to be precise, so-called residual networks, which are a subclass of feed-forward neural networks. And in this work, together with Krista and Martin Larsen, who is now at Carnegie Mellon University, we actually could speak about the ability of deep networks to approximate certain functions on state space just by a theory of dynamical systems. And actually a theory of dynamical system where the vector fields are chosen in a random way. So I don't want to go into detail here, just mention these controlled ordinary differential equations are in several respects interesting models for objects appearing in machine learning. And even if you're considering feed-forward networks, you can consider them as, or deep feed-forward networks as discretizations of dynamical systems of this controlled ordinary differential equation type. This is not the theme of this lecture, but still, in a point of view, you should be aware these controlled ordinary differential equations are an interesting class of equations which are models in many respects for interesting procedures in mathematics or its applications. But what we are interested here is actually to fix the initial value, or at some point y in the state space, and to consider the map from U to the solution of the equation possibly composed with a linear map. So this is one aspect which we are considering here. And this composition and the vector fields which are there, this is now abbreviated with W. So this is the linear map, and the solution y of the differential equation now I already write as evolution itself, as an evolution operator. And at time little s, I start with y, this evolution. So we are interested actually in understanding this map. So the map from y to this solution after time t minus s, when I start at s, possibly composed with a linear map. And again, when you take here a discretization, and when you ask yourself, given that the vector fields are neural networks, how this object would be caught in machine learning, you very quickly come to recurrent neural networks or long short-term memory neural networks. So actually objects which are well known in machine learning. So you see again, controlled ordinary differential equations are an interesting continuous time model for algorithms or architectures which appear in machine learning in order to do tasks. In this case, the tasks are prediction tasks or time series tasks. So tasks where you do not have a fixed dimension of the input space, but the input space has a dynamic structure, a structure of a time series itself, like U also has the structure of a curve, and you can continue the information streaming in by just moving on in time, and you can also continue this curve here, which is then the output. And you also have this adapted structure that the point where you arrive in t depends on u and its past, but it does not depend on the future of u. So this is very much in line with what recurrent neural networks or other of these time series techniques do in order to learn certain tasks. So this is the theme of the lecture, to understand such maps, and U will be actually in the lecture a very general object. So we said when you have calculations, most of the time you can think U is the C1 curve. But you should also, and we will have one instance there, think about U being a semi-martingale, a general semi-martingale. including jumps. And U can also be a rough path, a geometric rough path in most of the calculus I do, but it is actually a wide range of different objects which you can insert for U, giving different insights, and then as one can apply it to different types of applications. Okay, so this is first somehow just the setting. We are thinking about those controlled ordinary differential equations. We fix an initial value, and we are interested in the map from U to the solution of the controlled ordinary differential equation, possibly composed with linear map W. And I introduce now the paradigm of reservoir computing from the point of view how one could learn such a type of map, U going to W composed with the evolution of the system. So therefore, I use my most beloved technology being the board here. Is it visible, Julia? Can you see the whiteboard?
Yes, yes.
Very good. And you see also that I'm writing here.
Yes.
Yes.
Yes, no?
Yes, absolutely.
Yes.
We see it. Okay, very good.
Everything is fine.
Everything is fine. So imagine the following task, the following learning task. Somebody gives you a control. So this is this curve going to RD. And the curve is given to you on an interval 0t, t greater than 0. And you also know the solution here. Let me write it like that. I start at 0 and go to time s, and again you know the whole curve. So you know the input curve and you know the solution curve of the equation. What is unknown for you the VIs. You don't know them. You actually would like to learn them and to get an idea about how they are looking like. So this is in a very abstract way actually the task of time series analysis. Time series analysis very often can be understood in the following way, that you have a noise or just some non-autonomous driving force U, which is driving an evolution. This is what you know, but actually you do not know what the vector fields of the evolution are, and you would like to infer the vector fields from the observation that you have this input and you observe the output. Yeah. And when you think about many techniques in time series analysis, also in classical analysis of dynamical systems, have been developed in order to solve or to attack this type of question. How much do you need to observe given certain non-autonomous effects in order to understand the characteristics, the fine structure, the differential equation of this evolution? So when you think about it, actually, since the very days of Newton, and even before talking now in Pisa, since the days of Galilei, a lot of coming up with differential equations actually is an inference of observations, and the observations have been analyzed in order to come up with certain vector fields, which then do the job to explain the evolutions and which then follow some basic principles and so on. But in principle, we are always following such a path. We have some observations and we would like to know something about the vector fields. And machine learning is providing here techniques which are non-parametric from the point of view of classical inference. So you somehow just parameterize those vector fields, let's say by deep neural networks, depending on some parameters, and you try to learn the parameters in order that given the parameters given you actually reproduce as good as possible with respect to some loss function, the evolution which you observe. So this would be a classical recurrent neural network or machine learning approach to that. And reservoir computing in turn does something different here. And I just want to introduce it here first time. And also so we have this curve, we have this unknown dynamics, depending on you, with a fixed starting point. And reservoir computing says, map actually the curve to another dynamics, to the output of another dynamics, and this output of another dynamics is called the reservoir, which is again a curve like that one, but a curve which actually has nothing to do with this particular evolution here. It is just going to a usually moderately high dimensional state space and producing a curve here and in every component, and then apply to those curves which you have produced in this state space a map W. Very often this is a linear space, so this will be a linear map, a map W, which actually which is trained, which is chosen specifically, and this map W then has the goal to reproduce this dynamics by just linearly combining the outputs of these reservoirs. And actually, it is claimed in the very first articles of reservoir computing, even though there the situation is a little bit different, but still, let's say one can crystallize one philosophy out of it, and this is the philosophy I present here, that actually having a generic evolution, which you do not know, which is unknown to you, you can decompose, at least approximately, this generic evolution into a map which is evolution dependent, so which you have to learn. This depends on your data, and something which does not depend on your data, which depends just on the way how much expressibility you need given you in order to reproduce this evolution. So this is the so-called reservoir. And for the people familiar with machine learning, you would say this is a universal feature extractor. So you take U and you map U to a high dimensional linear space, and the vector which you obtain are the features. And these are again curves. And then you take linear combinations of those curves in order to produce that. The interesting thing in reservoir computing is that actually this feature extraction is claimed to work by a randomized procedure. So this is in contrast to many assertions in machine learning where you actually say feature extraction is very often depending on which task you need to solve. And then it is done in a somehow, it's designed. So you know this is a task you would like to learn, you know this you would like to learn, this map here, and therefore you extract certain features, and you do actually not do that in a random way, but you rather believe that there's a certain design you have to make. This is then the architecture of the networks in order to obtain a good expressibility here. And the claim of reservoir computing is up to some hyperparameters which are tuned, the dimension and the sort of randomness you inject, actually one can choose this reservoir in a very universal way, so working for many different tasks and in a random way. And when I heard that first time, it was my friend Juan Pablo, whom I know since more than 20 years. When he explained me about that, I was actually very skeptical that this has a chance to work. But after several discussions and also several thoughts which connected to earlier pieces of work I did in my research, I actually could convince myself that it is actually a very natural thing to have. Yeah. At this point, I ask, are there questions in the audience? Julia?
Yes, so there is one question.
Yes, please.
And the question is by Boumedienne, and they say if there are some links with the random Fourier features in the kernel method.
If there are links of this method with the kernel method, at this point, no. And I would even go further. I would say as classical kernel methods are described, no. Because one particularity of reservoirs is that reservoirs are just the evolutions, just like the evolutions, they are dynamical systems. So the reservoir also is not just a map, which is a feature extractor, as you would have it with reproducing kernel Hilbert spaces and kernels. It is a dynamical system. So it is a solution of a certain structure which is similar to the type I showed before. It's a controlled ordinary differential equation, but with random vector fields. In that sense, no, but it is certainly an ongoing research to look at, I give now a funny wording for it, spatio-temporal kernels, which have a dynamic structure themselves, and to relate that to reservoir computing. But this is ongoing research, so I'm not aware that there are results which I could quote in this lecture which relate to our results here, even though I think there might be some. Yeah, maybe Juan Pablo can say more about that, but in principle there is a difference between these methods. Does this answer the question?
Yes, thanks.
Okay. So this is reservoir computing, and let me return to this. Just I'm always a big fan of let me. I'm always a big fan of looking at original literature. So just because I mentioned the word, it's very worth for everybody here in the audience to take a look at the first paper where neural networks have been introduced. This is 1943, the early days of von Neumann computing architectures, and people tried to mimic brain activities within von Neumann computing architectures, and one of those people were Warren McCulloch and Walter Pitts, and they wrote this, you can imagine, very well quoted paper, A Logical Calculus of the Ideas Immanent in Nervous Activity, which actually leads to this concept of neural networks. It's very interesting to read, and it's also interesting to see how different this at these very early days of artificial intelligence, there was a lot of fantasy there for artificial intelligence, how different artificial intelligence was seen at this time, and what actually a neural network was supposed to do, and how people thought about brain activity. Very different from today, still very interesting to read. And by the way, it's a beautiful paper. It's extremely well written and just interesting to read. So I really recommend to take a look there, because I mentioned neural networks in this introductory chapter. And the second work, which I like to show you, it's also just worth taking a look. How was, do you see that? Julia, do you see this?
Yes, yes.
So this is one of the early papers of reservoir computing. And when you see here also the abstract, we present a method for learning nonlinear systems, echo state networks. And this is precisely the task we are asking ourselves. Echo state networks employ artificial recurrent neural networks in a way that has recently been proposed independently as a learning mechanism in biological brains. The learning method is computationally efficient and easy to use. This is because, as I said before, the reservoir is actually chosen randomly and exogenously. So you do not have to train that, and therefore it is, of course, much cheaper to do the training. The training is just regression. And what Herbert Jäger, one of the founding fathers of reservoir computing, then suggests is here in this particular paper. This is a paper dealing with chaotic time series. So where the map from U to the output has chaotic features, where they improve with those techniques, those learning techniques, by a factor 2,400 previous numerical analysis techniques to do predictions. And this is, of course, a very important paper. It's almost 20 years old, right? It's 2004. And it's also very worth a read. And also compare it to the paper of McCulloch and Pitts. And again, you see this fantasy about how the human brain works, how energy efficient the human brain works, and what one would like to do with those architectures which are proposed in order to solve certain tasks. So it's a second paper I really recommend you to read and take a look.
Joseph?
Yes?
There is another question.
Please.
Okay. It's by Riccardo Rupi. Can this be related with the feedback linearizations? It seems like the reservoir is a linear space in which then compute W times RU to stabilize the dynamical systems, for instance.
Stabilization, one would need to define what that precisely means, but in this part, there is a linearization going on, and we will very precisely speak about that in an hour, in which way we linearize a system. And the reservoir is a dynamical system whose output allows to write regressions, which can approximate up to an arbitrary degree of accuracy the given dynamical system. And that's, of course, a linearization, because it is finally a regression what we are doing. So in that sense, the answer is maybe we postpone the question a little bit, and then we can precisely tell how it is. And I think it is related to the concepts suggested by Ricardo. Is that okay as an answer?
Thanks.
Very good. So let me continue after this short excursion to the literature. And yeah, so this is the paradigm of reservoir computing split the input-output map, which I have been describing before, the map from U to the evolution of an unknown dynamic depending on U, split the input-output map into a generic part, which is called the reservoir, and which is not trained, and the readout part, which is trained but linear. And there are two features in reservoir computing. First feature is the reservoir is numerically very tractable. So it is easy to calculate the reservoir. And second, the readout usually is, or very often is linear. Not always, but often is linear. So in that sense, there are two aspects which make it attractive from a point of view of computational efficiency. Regressions are easier to solve than nonlinear regressions. Linear regressions are easier to solve than nonlinear regressions. And the tractability of the reservoir of this dynamical system actually is allowing to calculate this regression basis in a very efficient way. So these are two attractive features. And this goes even a little bit further, and one should see that as an important feature as of reservoir computing. Since they are not depending on the actual learning task, you could also do something which comes with different names in different areas. But basically it means you can also realize reservoirs physically or biologically. This has not been done yet, or not that I'm aware of that. But there is no reason why you need to calculate the output of a reservoir by von Neumann computer. Why you need to consider this as something which you can calculate by a von Neumann computer. You could actually have any sort of device, be it electromagnetic, be it optical, be it biological, which takes an input and produces an output which has these features of reservoir which you would like to have, so to be a sort of random dynamical system which is in a non-linear way processing U, and then train on these outputs, reading them off with some observations, the map W. This, of course, is now entering a really new area of research, when on the one hand, if it is realized as an experiment, a physical experiment, it allows for ultra-fast evaluations or calculations of the reservoir, but it also allows for very energy efficient evaluations. So this means you are, if this physical realization, if this is done in an energy efficient way, you're actually possessing a tool which is producing the features you need in order to do the regression, which allows you in a very cheap way to produce those features and then just to make the regression on it. Completely different order of magnitude of energy consumption in comparison, let's say, to a classically recurrent neural network which you train, where you need a cluster of computers in order to do the training, and actually quite a high energy consumption. And it is even having something additional, which I did not mention before. The reservoirs can be used for different tasks. So they do not really depend on the dynamics which you're trying to learn. So as I said before, the reservoirs are maybe not fully, there is some fine-tuning necessary, but they work for many dynamics. There's a sort of what in machine learning is called transfer learning. What works for one task also works for another task by just retraining the W, but not by retuning the reservoir. And this also is something which we also observe in the human brain. The human brain is not rewired when you get a new idea completely, but just the wiring of the human brain is used in order to store and work with new observations which you make. And what is also very fascinating with reservoir computing, it works unreasonably well with generalization tasks. So generalization task would just mean in the picture which I had before, I have one U, I map it to the output, the evolution. I split this map into the reservoir and the trained W. Then I have the W, I store the matrix of regression coefficients. And then somebody comes with another U, completely different curve. And then you can say, okay, in order to predict the value of the evolution along this different U, you could now just take the different U, map it into your reservoir, take the regression coefficients which you learned before, and make this prediction. And it is provable that in many circumstances, this works very, very well. This is actually what this Herbert Jäger is alluding to by saying that this numerical technique which he proposes, or which they propose in this work, actually these numerical techniques beat classical techniques by orders of magnitude. Okay. Let me, in the first step, convince you that actually reservoir computing makes sense from a classical mathematical perspective. And I will not fully construct reservoir in the very sense what I used it before. So it will not be a very tractable reservoir which I construct, and it will not have random features, but still it will be an object which has this property that it only depends on you and does not depend on the particular dynamics. And it allows to represent the dynamics in approximative way up to any order of accuracy. So this is actually what I'm going to talk you through in this next section. This is signature as abstract reservoir, even though one should put reservoir under quotation signs, because it is not a reservoir in the very sense meaning of the word. So we consider a controlled differential equation. As before, we have some vector fields, and for simplicity, think of E being some Rn, but you can also think of a manifold. The vector fields are tangent objects, and we have a differentiable structure there. And just that you have a little bit of fantasy, so U can be a Stratonovich-Brownian motion, it can be a finite variation curve which is continuous, it can be a rough path, it can be a semi-martingale. I only use here first order calculus, and therefore I always assume that I have, when I talk about a semi-martingale, I have continuous trajectories and the Stratonovich integration applied here in order that my calculus is first order for the time being. In any case, this describes a controlled dynamics in E controlled by U, given the vector fields and given then the output Y. And as we said before, we would like to learn this map from U to Y, which is a complicated nonlinear map. Obviously, a complicated nonlinear map. So it is nonlinear by the very construction of the what it means. And it is complicated because you can relatively easily prove, for instance, if U is a Brownian motion, that the map is definitively not more regular than measurable. So this is a well-known statement actually going back to Itô, that if you have a two-dimensional Brownian motion, for instance, and you consider certain simple vector fields which have a simple structure but a certain non-commutativity, then it is clear that the output Y of this map will only depend in a measurable way on the input U. So it does not depend in a continuous way. It's provably not continuous. This has to do with the fact that on Wiener space, stochastic integration is not continuous with respect to the topology on Wiener space. And this has to do with the fact that you are actually integrating here along integrators which are not of finite total variation. Brownian motion is not of finite total variation. It has with probability 1 on every interval an infinite length, and therefore there is no hope to get a continuous map depending in a continuous way on the input signal. You also see that you see a loss of derivatives as very quickly when you do the estimations. So when you look what happens when you are changing the input signal a little bit to the output signal, and you change it in a way which is related to the uniform topology on the input space. For instance, you can replace, let's say, U being just time, you replace it by something which is very close, but it is moving relatively quickly around the line time, then actually the solution of your differential equation might move relatively far apart. No continuity with respect to the uniform topology, even though uniformly the two trajectories are closed. It actually depends on the first derivative, the continuity. And this fact, this well-known fact in dynamical systems, makes the theorem that actually it is a nonlinear map which is complicated, so has a very low regularity. Yeah. Therefore, it's not easy to learn it. Therefore, it is interesting to do the following construction, which is a non-commutative version of Taylor expansion. I use here some abbreviation. The abbreviation is I use the so-called transport operators. So if f is a function from state space to the real numbers, a smooth function, a test function, you can think of a test function in the sense that it belongs to a class which is point separating on your manifold. So the vector field applied to that function is just the directional derivative of the function, the direction of the vector field at any point x on your state space. And this identifies, of course, the vector field when you think about it. And therefore, you can say either you talk about the vector field as tangent object, or you talk about the vector field as a first-order differential operator. It's a well-known identification, a categorical identification you can do in a differential geometry. And we shall use this representation of vector fields as first-order differential operators in order to facilitate the following calculation. So we have a controlled differential equation as before. Instead of the y, I write now evolution. And the claim is the following: if I have a smooth function f, which I apply on this evolution, so I test at time t how what happens if I insert the evolution into my test function, then I can write this as a double sum. The first sum goes along a degree from 0 to m, and the second sum goes for every degree on all possible choices, and there is a little mistake here, there should be an ik, all possible choices of component indices I, and they determine these iterated integrals. So you integrate here between S and T, component I1 of my control U, T1, and then you integrate it up to T2, and then you integrate it against component I2, and so on. You get all those iterated integrals. By default, they are different. If you change the order I1 to Ik into another order, if you make a permutation, it is in general a different object what you obtain. And as a coefficient, you have here a number, and the number is just apply the vector field Ik to F, apply the vector field Ik minus 1, and so on up to I1, F, and evaluate at the point X. This is the statement of this non-commutative Taylor expansion theorem, and there's even a remainder term here, and the remainder term can be written like that. Yeah. And again, I made the same mistake here. It should be an IM here. This is work going back to the 50s. Teichmann was working on that in algebraic topology a lot. Gérard Benarous in the 90s used those expansions in order to talk about hypoelliptic diffusions. Terry Lyons in the 90s, Gérard Benarous was in the 80s, Terry Lyons in the 90s, is building a rough path theory on this expansion by extracting certain ideas out of these expansions, how to define rough paths. And then the work of Peter Fritz and Terry Lyons is building upon this expansion. And finally, also one of the Fields medals, which were awarded in the last years for Martin Heira, is also, let's say, when you look at it from the point of view of rough path theory, which is building upon this expansion, also related to this non-commutative Taylor expansion. So let me give you an argument why it holds. So it's one of the very important theorems in analysis, which actually has a very easy proof. And still it provides a structure which is fascinating in many directions. It's a structure which is remarkably complicated, and you need deep algebraic tools in order to understand it fully. And it's also remarkably applied and practical. So let me prove this statement for you, and you will see the proof is very easy. I stop here the sharing. Is there a question? No. People are speechless. Very good. You can see that, Julia?
Yes.
Very good. So I have my differential equation. Let me allow to write it again with t. So I go from s to t. I start at time s with y, and then I have the d dimensions here, and I have here the integral from s to t, and here I have the vi applied to f, y s r d u I r. So what I did here is nothing else. I take the differential equation for y. I apply a function on the differential equation, and I write this function applied on the differential equation as an integral by just calculating the derivative. What is the derivative of f applied to the solution of the differential equation? This is the directional derivative of f in the direction of the vector field at the point where the differential equation just finds itself, and therefore I know how the integrand looks like here. This is just the fundamental theorem of calculus, which you have learned many years ago in your calculus course or even before in high school. So this holds for every f in the test functions. Let's call the test functions C infinity E. And then every practically thinking person says, okay, the left-hand side is a test function applied on the solution of the equation. This is the test function applied to initial value plus sum, and then I have another function applied to the solution of the equation. So therefore, you could insert the equation into itself. You could say, let me write this guy here as VIF at the initial value plus integral from 0 to r, because here we only go up to time r. Now, yeah, and then I have maybe a Vj applied on VIF. And let me just put that away. I don't need it anymore. You know it already. And this is applied on, now I'm getting out of letters. Let's call it R tilde. And I have D, J, R tilde, and this goes up to R, and this is inserted now here into that, and then you see suddenly, now yeah, this is a constant, so the integral is just integral from s to t dui, and here you have a double integral now. And when you look at that, you see already this is the expansion up to m equal to what I wrote before. Now again, you have a function here. You insert the equation into itself and you get a triple integral. And you get here a double integral out because you have always a constant part and so on. So it is just inserting the equation which you have for test functions into itself and you obtain this expansion. This is actually the proof. The rest is just ordering things, since you do not know whether iterated integrals for different permutations of I1 up to ik are different. You just give for each of them a different object in the sum, and you sum over all of them. Yeah. So this is the proof of this statement. And let me just show you one very simple example that you feel very comfortable and know very quickly why it is actually called the Taylor expansion, a non-commutative Taylor expansion. I take now a very simple example. I take my state space to be R. I take the vector field V1 to be constant. I take my curve U of t to be just time. And I only have one, so I take d equal to b1. Yeah. Then everybody who is sitting in the audience can solve this differential equation. This is just the differential equation which has as a solution t, y of t is actually y plus t. This is moving with a constant velocity 1 to the right, and therefore the solution is y plus t. Now let us take now a test function, and I apply it to the solution. And our theorem would say, so this can be written k from 0 to m. Then I have the directional derivatives of f in the direction of the vector field. What is the directional derivative of f in the direction of the constant vector field? Now, yeah, this is in civilized countries just the derivative of the function applied k times at x. Because the directional derivative of a vector field with length 1 is just the first derivative, and then if you apply to that another times then you have the second derivative and so on. And here you have now the iterated integrals from, let's say, 0, t1 up to tks. So this is dt1 up to dtk. And also here in civilized countries, it's very clear what this is. By the way, there's the remainder term. So this is just k from 0 to m, k's derivative. And here you have t to the power k divided by k factorial plus remainder term. And everybody knows that this is called the Taylor expansion of a smooth function. So therefore, in the simplest case, this is just the Taylor expansion of a smooth function. But it's a non-commutative version of it for different vector fields. By the way, also a relatively beautiful proof of the Taylor theorem, because it gives you right away the most natural remainder term, which you should consider from a dynamical system point of view. And it is just coming from inserting the equation into itself. Is there a question at this point?
No.
Okay, very good. So we return. So this is the theorem. Yeah, this is the theorem, this beautiful non-commutative Taylor expansion theorem, expanding the action of a test function on the solution of such a differential equation into iterated integrals multiplied by certain coefficients. Now, take a step back and think of reservoir computing. Reservoir computing also says that you can write, let's take f to be just one component of your evolution. You can write the image curve, the value given u, you can write it as a regression of something which does not depend on the particular dynamics. Only the regression coefficients depend on the dynamics. Here you would see this is precisely what we have in reservoir computing. We have something which does not depend on the dynamics. This is just depending on u, so these are the features. And this is only depending on the dynamics, but does not depend on u. And in that sense, that's precisely a paradigm of reservoir computing, except that the vector of all iterated integrals is a complicated object, and it's a high-dimensional object. And second, we don't know how good this regression is. So it might well be that the condition number of the regression is actually not great, and therefore it might be difficult to learn the regression coefficients. But in principle, you could say this is an instance of reservoir computing, but maybe a little bit far-fetched. Let me work a little bit on that to make that more precisely. And here I actually would like to invite you to take a 15-20 minute journey to abstract algebra. This is what I referred to before. This is Bourbaki style abstract non-commutative algebra, entering here a lecture which is actually dealing with machine learning concepts and reservoir computing. So the goal here for this abstract algebra is not to impress you by some knowledge. It is just saying, if we want to talk about iterated integrals, there is one natural playground to do that, and the natural playground are so-called Hopf algebras. I'm always very happy and proud to talk about them because it is Heinz Hopf who invented them, and after him they are named. It was in the field of algebraic topology in the 30s and 40s, where there was a lot of activity. And Heinz Hopf was a professor at ETH, therefore I like it very much that me also being a professor there, I'm talking about concepts which have been developed in this beautiful building, which I'm in the moment actually not seeing very often. So they have been developed in this beautiful building by Heinz Hopf. And let me explain you why it is extremely natural to consider these iterated integrals, which are the regression basis for the action of a test function on the dynamics, why to consider these iterated integrals actually within Hopf algebras. Therefore, we introduce a particular Hopf algebra. It's one of the simplest Hopf algebras which you can consider, and this is the Hopf algebra of formal power series in non-commutative indeterminates, which are named E1 up to ED. So if you feel uncomfortable with the wording non-commutative indeterminate, which is, when you are an algebraist, this is very natural for you. So this is just a free algebra generated by D generators. If you're not an algebraist, you are somehow a little bit reluctant of thinking, what is that actually a non-commutative indeterminate? So this is a variable which has a certain prescribed number of relations. And here the relations are just that you have associativity, but you do not have any commutation relation, and you can multiply and add the guys there. So think, for instance, of a matrix of some dimension where you don't know anything about how it commutes with other matrices which appear here. You have D matrices and no information about how they commute. So you just have to write the products of the matrices as they appear like words, and if you have a permutation, it's a different object. And we consider all former linear combinations of this, and we call it non-commutative formal power series in these D indeterminates. So they are written in the following way. You have coefficients ai1 up to ik. You have these monomiers ei1 up to eik. These are the products of the indeterminates. And you write this infinite sum formally here. Of course, formally actually does not mean anything. This is a semantic way how to write things. It just means that you have a coefficient vector which is indexed by I1 up to IK, and you think about this being a coefficient of a non-commutative power series, but you have no information about the convergence of this series, and it's also not important if you just consider the coefficient vector. And of course, if you just have that, you can say at least sums are possible. This is just summing component by component, and also products are possible. This is just having a product of two sums gives you with this type of grading here by just reordering the sum, a natural way how to define a product. If you want to talk about the topology, which does by no means make things convergent, it's just a topology on the set of coefficients on this sequence space, then you can take the locally convex topology, making all projections of A onto each component continuous. And this is a nice locally convex topology in order to guarantee that you can talk about smooth curves. If we can talk about smooth curves, we can talk about dynamical systems. In the sense I was talking about before, a dynamical system comes with a vector field, and the vector field, if it has certain properties, then we can solve it. Ask Stefano for the conditions you need here. So let us introduce some vector fields. The vector fields which we can introduce on the algebra, there are D canonical guys. the one that's here, the vector fields multiplication from the right or from the left, but here we take from the right by EI, by these generators. So this is just take an element of the algebra and multiply it from the right with EI. In the representation of the element, this just makes this guy here a little bit longer. You multiply EI in that here, and you have again a sum. It's just, when you look at it from the point of view of the sequence space, it's just a shift in the indices of the sequence space. Okay, and then you can say, if I have vector fields, if I have a control, if I have a differentiable structure, I can look at the dynamical system and ask whether it can be solved. The dynamical system has a name, it's called signature, and this is a dynamical system which takes values in this algebra of former power series generated by E1 up to ED. And the dynamical system comes with the vector fields as we have it before. Just as at the beginning, I'm so sorry. So signature is the element of the algebra. I multiply it to the right. So this is the vector field. Then you have D vector fields and you make a linear combination by the derivatives of the controls. And this gives the speed how the curve continues. And if you think about this dynamical system, you will very quickly convince yourself that you can solve it and that you can even write down the solution. The solution can be written down very easily. It is just the collection of all iterated integrals in form of a former power series where the coefficient a I1 up to ik is just the iterated integral of ui1 up to uik. It's just that. So the solution of a dynamical system actually appears to be here just the vector of iterated integrals which I had before in this non-commutative Taylor expansion. And now you can say with this statement, with this existence statement for existence and uniqueness statement for signature, which is algebra valued controlled ordinary differential equation, you can write now the Taylor expansion in the following way. Given a generic evolution and the test function and the order of accuracy m, you can find a time independent, I write time homogeneous linear map here from the algebra truncated at m. You can truncate the algebra and just take all products which are longer than m, which are of more than m factors, you set them 0, so-called truncated algebra. You can write the truncated, the effect of a test function on the solution of this unknown dynamics as a linear combination of signature, as we had it before, plus something which is of order t minus s to the power n plus 1. This was the remainder term. And here you see now signature in that sense of truncating the algebra is a high but finite dimensional dynamical system. I have a linear map which is applied to the outcome of the dynamical system. And this gives me the effect of a test function applied to the solution of this unknown dynamical system. So this now looks really like reservoir computing. In reservoir computing, you also have a dynamical system, the reservoir. This is this guy here. And this reservoir, you have to do something which is dynamic specific. This is the W in order to apply this linear map. And you can then approximate this quantity here up to this order of magnitude. So in that sense, signature is an abstract reservoir, and you are maybe convinced now at this point a little bit more that this generic idea of Herbert Jäger appears actually in dynamical systems in a very standard way, that you can construct dynamic independent, so universal dynamical systems on which regressions provide you with approximations of specific dynamics, specific but generic dynamics, up to a certain order of accuracy. Yeah. So that's signature as an algebra valued object, which gives you an instance of a reservoir. Yeah. Let me just talk a tiny little bit more about some properties of this algebra and why actually it is a Hopf algebra. So what is a Hopf algebra? A Hopf algebra is an algebra with the additional property. It's not a full definition here, but it's an addition, the additional property that also the dual space of the Hopf algebra. Dual space in the algebraic sense, so you have the Hopf algebra. An algebra is also a linear space has a dual space. This is the algebraic dual, let's say the linear function as you can write on this linear space. And the dual space is also an algebra. Yeah, the dual space is an algebra and the algebra is an algebra. So you have actually structures on this algebra which look like multiplication, but the arrows are reversed. You know, when you go to the dual space, all arrows are reversed. And these are called co-multiplications. So actually you have a multiplication. This is the multiplication you have in the algebra always. Take an element A1 and take an element A2, and this gives the product A1, A2. But you also have a multiplication on the dual space. So this takes a linear functional and the linear functional maps it to a linear functional. And when you dualize this multiplication on the dual space, you get an object which takes an element of your algebra and maps it to an element in somehow the bilinear maps. And this is called the co-multiplication. And the algebra has therefore not only the multiplication, but also a co-multiplication. And if the co-multiplication is an algebra homomorphism in a certain sense, if there are a couple of properties satisfied, actually you obtain a Hopf algebra. So Hopf algebra is easy to remember. Algebra and also the dual of the algebra both carry compatible algebraic structures. And the beauty of those concepts actually comes from the fact that you have a couple of very natural objects inside Hopf algebra, and one natural object is the so-called group-like elements. You can formulate them with the co-multiplication, so the product on the dual space. And the group-like elements actually form a group, which is not by chance, but this group has a very, very beautiful property, which also gives a completely immediately a meaning to the whole story. The group is a subset of our algebra and a nonlinear subset of the algebra. And you can, of course, of every subset of the algebra, you can say, okay, I consider the linear functionals on the algebra just on this subset, restricted to this subset. And I just look at the linear functionals, and the linear functionals go from the algebra to the real numbers, and I just restrict these maps from the algebra. I restrict it on the group. So this gives me actually a subset of all possible functions on the group, namely linear functionals restricted to the group. Now, you can ask yourself whether it is possible that if you have a linear functional L1 and a linear functional L2, to express what happens if I multiply those two functions. And the beauty of the Hopf algebra is the following thing: if you multiply those two linear functionals, then of course on the whole algebra you'd get a square. You get something which is not a linear functional anymore, because if you multiply a linear functional with a linear functional, the result is not a linear functional but something which is a bilinear object. But if you restrict this bilinear object again to the group, then actually you can express it as the restriction of another linear function on the group, and the other linear function is just the product on the dual space of L1 and L2 restricted to the group. So you have a very precise meaning what the product on the dual space is. It just gives you the linear functional which represents the product of two linear functionals restricted to the group. Not outside, but on the group. And this very intriguing algebraic structure, you can develop a lot of theory, go to the internet, go to the library, take your most favorite Bourbaki book or any other book on algebra and read a little bit about Hopf algebras. They have very beautiful properties. And actually, this is also a property we have for the former power series in these non-commutative indeterminates. What does that mean? If you think about linear functionals on the group being multiplied with another linear functional, that they are actually restrictions of a third linear functional on the group. This means that the set of linear functionals on the group is an algebra. The set of linear functionals restricted to the group is an algebra, and therefore dense, if you take a corresponding topology, in the set of all continuous functions on the algebra, on the group. So this is a very beautiful property which usually you do not have, that linear functionals restricted to a nonlinear subset of some linear space actually form an algebra. And this is one of the important properties of Hopf algebras. Okay, now what does this have to do with our signature? This was an algebraic story which might have a lot to do with algebraic topology, but what does it have to do with signature? Now it is, when you start thinking like that, relatively quickly clear that actually signature, if you start it at 1, the solution of this dynamical system, actually signature takes place, takes its values in this group. So you can prove that signature takes always, for any time, values in the group. It's a path which is taking values in the group. It's not going everywhere in the algebra, it is lying in the group. And therefore you can think now of linear functionals restricted to the group, signature lies in the group. So at time t, I have a certain element of the group, and I apply now a linear functional L1. For instance, just take component number I1 up to ik. So I get an iterated integral as the output of the linear functional applied to signature time t. And I multiply that by another linear functional. This would be another iterated integral. So this just says products of iterated integrals are actually linear combinations of iterated integrals. So this means the set of all iterated integrals is an algebra, which is, from the point of view of analysis, just a consequence of Leibniz rule. But you see it here in this very abstract setting, and actually you can play with this abstract setting to get more general instances of this. But here it is just mentioned that it is not only worth considering the algebra to understand signature as a dynamical system, it also allows you immediately to see that products of iterated integrals on the same time interval are an algebra. So products of iterated integrals are linear combinations of iterated integrals, and you also have the flow property or the evolution property if you take signature from S to T, and if you take signature from T to U, and if you multiply that appropriately. So signature TU multiplied with signature ST is actually signals from S to U. So you have these two properties, and these two properties allow you very quickly to understand that actually it is a beautiful algebra on path space of functionals which you have constructed to approximate solutions of generic dynamical systems. So this is the Hopf algebraic point of view there, and I also invite you take a look at the original papers, and if you want to do a favor to yourself, let me look at that. I think I also opened it here for you. One of the beautiful classical papers. So, Revista Matematica Iberoamericana, 1998. This was a year-long project, differential equation driven by rough signals of Terry Lyons, a beautiful 96-page paper. And in this paper, actually, you see our friends, the controlled ordinary differential equation, and you very quickly will see also this expansion with respect to signature, and a lot of insights there, and also the Hopf algebraic structure and so on. Very beautiful paper to read, and the starting point of rough path theory and rough analysis. Yeah. So also here I recommend read the original paper. It's very insightful and interesting to take a look there. Okay. Is there a question? No.
No, there are no questions.
No questions. Very good. So actually, this is maybe a good point to make a little break of 5 minutes for people who would like to have a little coffee or discuss something. Is that okay?
Yes.
Sure.
Yeah. So I will then continue after understanding that the signature is an abstract reservoir, how to construct a true reservoir out of it. But I will also introduce a semi-martingale version of signature, which is actually a new result, which might also be interesting for people who have already seen this talk to some extent. So I start with semi-martingale signature after a 5-minute break, and then I continue with the construction of true reservoirs and some applications. So I come back in 5 minutes, right?
Okay, thank you.
Very good. You can also stop the recording if you, or I don't know how you do that. You just leave.
We can pause it, but then we should remember to make it start again.
Yes, this is true. Yeah, right.
Okay.
Can you hear me, Julia?
Yes, sure.
I'll come back.
Yeah. So you can switch on the recording now.
I have switched the date.
You did already?
Just 2 seconds ago.
Okay, very good. So we understood before the break that signature can be understood as a Hopf algebra valued dynamical system, and it is a universal dynamical system in the sense that it does not depend on a particular dynamics, but if you take those curves which appear in different components, the iterated integrals, and you take linear combinations of those curves with specific linear, numbers, then you can approximate the components of any dynamics, generic dynamics, up to a certain order of accuracy. So this is somehow the non-commutative Taylor theorem you have there. And before I go into references to the literature, referring in particular to the working group of Terry Lyons here, I would like to show a semi-martingale version of that. So for the probabilists in the audience, who might be some, this is now a beautiful encounter of one of the beautiful objects in stochastic analysis and probability theory. This is the semi-martingale. So this is the probabilistic generalization of a curve of random variables with respect to which integration is still possible. So from a point of view of classical stochastic analysis, you would say this is the roof concept for discrete time processes, Brownian motion or martingales, and finite variation curves. And let me just 5 minutes introduce what a semi-martingale is, and then talk about signature for semi-martingales. This is not just the mere generalization of the concept which I have before. You have to imagine one of the important assumptions which I was having before when I constructed signature for this generic dynamics was that we have a first order calculus. The first order calculus comes to, it's important when we take this iteration. In the iteration, you just see the first derivatives, the directional derivatives of the test function with respect to the vector fields. Now we know if we have a continuous trajectory semi-martingale, actually by taking the Stratonovich integral instead of the Itô integral, you can make the calculus related to this semi-martingale first order. That's easy. But if you have jumps, there is no way to make it the first order calculus. I mean, there's one way which is called the Marcus integral, but this is a way you would somehow probably see with some skepticism. Namely, it just interpolates linearly with infinite steepness a jump as a continuous curve. So it just says we have a jump of a stochastic process and we draw a line here which has arbitrarily large steepness, get from one to the other point. And you can make a calculus out of that, and this is called the Marcus integration calculus. So the question which I asked myself and which a couple of friends have been asking themselves, and in particular within the rough path community, is the following. Can we write down a concept for signature where we deliberately stay beyond a first order calculus? And in particular, we have jumps. Of course, beyond first order calculus, but without jumps, this has been done. This is the theory of so-called branched rough path, beyond the geometric rough path, and the beautiful theory which has been initiated by Massimiliano Gubinelli, who is now a professor in Bonn, and also Martin Heira, and several people have been working on it. But the real question, how to include jumps, this has only been recently in the rough path community addressed, and work by Peter Fritz and also David Prömel and Zhong Liu have been contributed there. And what I show here is somehow a probabilistic counterpart to that, a concept of signature which one can relatively naturally write down in this stochastic analysis setting, and which does the same job, even though it looks different to the things which you would have in rough path theory. But Let me first introduce what a semi-martingale is and then write down what this does. So what is a semi-martingale? We need three spaces in order to define semi-martingales. We need the space of CAG-LAT processes, we need the space of CAD-LAG processes, and we need the simple predictable processes. You know, stochastic analysis is a French discipline, and therefore there are many abbreviations, long abbreviations. CAD-LAG. What does CAD-LAG mean? Continue à droite, limite à gauche exist. So these are right continuous, left limit, adapted processes on the real numbers, on the non-negative real numbers, taking values, let's say, in RD. And what are CAG-LAT processes? You can already imagine. This is continue à gauche, limite à droite exist. So these are left continuous, right limit processes. So it just means when you draw the curves, right or left continuous, and the limit at the right or left-hand side exists. And what are predictable processes? Predictable processes are piecewise constant processes which are having the following structure: HS at the point omega, omega and omega are probabilistic basis, S somehow in the time interval, which is the non-negative real numbers here. You write it as the sum HI depending on omega, and a characteristic function depending on stopping times Ti plus 1. And the stopping times are increasing, and the HI are FTI, so the left endpoint here measurable. And you see here piecewise constant and CAG-LAT. So there are left limit and the right exists. Yeah. So when you go into, we have left continuity and limits to the right exist here. Okay, so these are predictable processes, and then we have the left continuous right limit and the right continuous left limit. We have on those spaces, these are linear spaces, these are vector spaces, we have topologies, and on the CAD-LAT, CAD-LAG processes, we can consider the following topology. Take, let's say, two processes, right continuous, left limits. Then the metric distance between them is the sum 1 divided by 2 over n expectation of the running maximum of the processes norm and wedged by 1. So I cut off just the large values, the expectation of this. This is, of course, a finite number. And this just metrically topologizes the following concept of convergence. A sequence xn converges to 0 if and only if the running maximum of the process on an interval of length n, so from 0 to n, this is the running maximum up to n. The running maximum goes for every n in probability to 0. That's the concept of convergence on these spaces, and it makes those spaces topological vector spaces. And by the way, it's also from a didactical point of view interesting. This is one of the few examples in mathematics where a topological vector space appears which does not carry a locally convex structure, not to talk about the normed structure. It is only a topological vector space, but it's an important one. And if, let's say, if you are considering a time interval or just constants there, then this is just these are the random variables, and the random variables have the same structure. These are complete topological vector spaces, which are usually, if omega is generic, not locally convex topological vector spaces. And this topology is called the UCP topology, uniform convergence on compacts in probability. So this is topology in the right continuous left limit, on the left continuous right limits, and they are complete. The predictable processes, of course, are not complete with respect to that. Now, yeah, and what is then a so-called good integrator? A good integrator is process X, which is right continuous left limits. And the natural notion of an integral of A predictable process with respect to the good integrator is, of course, these finite Riemannian sums with the hi times the next increment over the interval where the h is constant, and you sum that up. And you call it a good integrator if the map from the integrands to the result of the integral is continuous with respect to the topologies I introduced before. That's somehow the minimal property you can demand of an integral. It just says if you have integrands which you can write down at integrals which you can write down as finite sums, and you make the length of the summation longer and longer, with the understanding that the predictable process converges UCP, so on the probability space in probability and with respect to the time interval uniformly, then the resulting outcome of the integral should also converge in UCP. So this is somehow a minimal notion that integration makes sense if you refine the gridding more and more. And all x which have this property are so-called good integrators. This is the so-called good integrator property. The beautiful and fascinating theorem is then following up, which is actually not so difficult to prove. It's relatively elementary to prove it. X is a good integrator if and only if it is a semi-martingale. So this means it can be decomposed into a finite variation process and a local martingale. Both directions are deep. So even the direction, if you have a semi-martingale, that the semi-martingale is a good integrator, is not completely easy. The difficult part is that not every local martingale is locally square integrable. Not every local martingale is locally square integrable. For square integrable martingales, this is just Itô's insight, the Itô theory. For non-square integrable, just L1 martingales, you have to dig a little bit further how to find that out, and that's actually elementary, but deep inequality you need to use here. That also martingales are good integrators. Finite variation is anyway a good integrator. This is the classical Lebesgue-Stieltjes integral, and the other direction tells actually these are all good integrators. So this is the Bichteler-de la Cherie theorem from the end of the 80s. No, sorry, from the end of the 70s, beginning of the 80s. Also here I recommend everybody to go to the beautiful lecture notes of Paul André Meyer, where these theorems and the reasonings behind are described. It is always a pleasure to read it, and a meditative experience, and also a beautiful experience to read into those notes, and also to see how different mathematics was written in those days. So there were no long introductions to papers explaining why it is applicable and why it is interesting and quoting many people. They just started after the title with, this is a probability space, this is the theorem, this is the proof. And the papers were, of course, shorter and written in typewriter. So Bichteler de la Cherie. Then you can introduce a second topology. This is the Emery topology. This is a topology which makes the set of semi-martingales a complete topological vector space by just taking inside additionally also all integrals with respect to bounded integrands. And you have this statement here. And the map actually then from the space of left continuous, right limit processes, which you get by extension of the continuous map, to the set of outcomes of integrals, which are semi-martingales again, is actually continuous, where you take in the range the semi-martingale topology. So this is the second theorem you have here. Good. Having that, one can right away prove the Itô formula. The Itô formula is the following formula. You take n good integrators, which we know already are semi-martingales. You take a C2 function, and then you can right away prove that if you insert the good integrators in the C2 function, you can decompose it in this way. I use here, by the way, Meyer notation of integrals. So this is the stochastic integral of the derivative of f evaluated at the left end point, there the limit exists, integrated with respect to dxi. And in Meyer literature, you always write a dot here. So this is first derivative, 1/2 second derivative, and this is the jump part. So that's the Itô theorem in all its beauty and generality for semi-martingales with jumps. And you see here impressively, this is definitively not a first order calculus. First order calculus would mean that actually you only have this part here, only the first guy. Everything else does not appear. And you can imagine Stratonovich gets rid of the second one by somehow normalizing the integral, but you will not be able to get rid of that. This is a part which depends on the jumps of the semi-martingales. The delta x, I, s are just the jumps at a certain point, and you will not get rid of the Stratonovich or not. So the question is, can we write down a signature object for general semi-martingales, for n semi-martingales, which does a similar job than signature? So you can write expansions of dynamical systems driven by the xi's, and it would be good to have those expansions also in terms of semi-martingale topologies, the topologies I introduced before. So it's the following statement: existence of semi-martingale signature. You are already now, as you would say in Austrian, old rabbits, so you know how this is done. You take a free algebra. The algebra is generated by all the guys which are of importance here. You take time, you take EI, so this is for the x1 up to xn. And sorry, I made a mistake here. There should be a D here. I have D semi-martingales. Then I have these covariation terms. There I introduce an additional indeterminate, Eij, and then I have products of jumps. And when you think a little bit about the first products of jumps, which are actually necessary in order to think about, here are the triple. So the monomials of order 3. So I take for every lengths of monomials L, I take indices I1, I2 up to IL. They can be ordered because this is commuting, these are just real numbers. And I introduce for each of them a symbol and indeterminate generator here. But I only have them for I lesser equal j lesser equal k, because there I have a commutative relation. And here also xi, xj is equal to xj, xi when you take the quadratic covariation. And then I write down the following differential equation now in the Meyer notation. So this is an integral, this is an integral. You could write in Itô notation a d here, and then you would have a dt here, and the dxi here, and the dxi, xj, and here you would have just the jumps. And I claim that this is a well-defined AD-valued process, and actually this is just a collection of all iterated integrals of xi with respect to itself, of the quadratic variation with respect to itself, and of the cumulative monomials of order 3 and higher of jumps. So actually here the input signal actually is infinite dimensional. It's x1 up to xd, the quadratic variation, time, and additionally also the monomials of jumps. But still, since my algebra so nicely spreads the different dimensions, I can each of these gets its own dimension, and therefore I have no convergence issues, and it is just having a solution, this equation, and it gives again an AD valued process, uniquely defined by this equation. And there's a second statement, which is more interesting. If you take now linear functionals of the semi-martingale signature, so these are just linear combinations of these iterated integrals with respect to the list of guys I had before, then actually this is an algebra of semi-martingales. So if I multiply two of them, it's a linear combination of others. And the closure of this algebra equals to the closure of all polynomials of components of the semi-martingale signature stopped at deterministic times. Yeah. So this is in a way a tautology, but I say here this sounds as if I prove something important, but actually this is nothing important. The only important thing is the definition and the knowledge that this is an algebra of semi-martingales, and I just say the closure is equal to something, and the something I describe a little bit differently. Actually, there's an open mathematical problem. I'm not able to solve it to describe differently the closure in the semi-martingale topology, but even in the UCP topology of signatures here. And so far, I did not succeed in that respect, which might be also topologically a slightly deeper problem. And the statement is actually, you can prove it as before. You just say you have the Itô formula, and in a way before when we calculated signature, also the first order calculus, so the Itô formula was behind it. And then you just say, you can make it a little trickier. Let's take f a polynomial. Then this is a polynomial of order degree -1. This is a polynomial of order degree -2. This is a sum of derivatives order 3 and higher with monomials of order 3 and higher up to the degree of the polynomial, because this is just the starting point of the Taylor expansion. So actually what you have here are derivatives order 3 and higher times monomial order 3 and higher. And therefore you can write the action of a polynomial on the semi-martingale just with integers, which you are allowed to take. And then you have here polynomials of a lower degree. And then you insert, as before, the expression of a polynomial by an integral into the integral, and you do that again and again and again. And finally, you have every polynomial of the semi-martingales can be expressed as a linear combination of iterated integrals. Now, yeah, and that's actually the whole statement. The only thing you have to understand is how to get rid of time dependence, and you can make a time dependence here, and the time dependence can also be polynomial. Then you get additionally integrals with respect to time. Remember, we have allowed that. So time also appears here, and then you can make the time dependence in a way such that you concentrate at a certain intermediate point, and then you get also stopped processes at a certain intermediate point as a possibility here. And yeah, this gives the statement. So this means that the semi-martingale signature are approximating a lot of processes which are polynomials of the process stopped at some time, intermediate time, and can be approximated by signature up to the end. Yeah.
Joseph?
Yes, please.
There is a question. Okay, there is a remark by Juan Pablo first about the first question of today by Vumedian on the dynamic kernel. So he pointed out two references on the notion of dynamic kernel. And the
yeah, I know that there exists this is related to this spatiotemporal kernels. where some
and
people
there are 2 references on the chat, basically.
Yeah. Okay.
And there is a question by Krista, and
Yes.
does the semi-martingale signature for pure finite variations on processes correspond to iterated Riemann-Stieltjes integrals?
If the semi-martingale has finite total variation but jumps, you still have that you have to add an infinity of objects here. If it were continuous without jumps, then this is would be precisely the iterated integrals, because then it's a first order calculus. But already for finite variation processes with jumps, it's a generalization of what you classically have. Does that answer the question, Krista?
Yes.
Okay. Very good. So this is a semi-martingale signature, and it's also beautiful here to see, in contrast to classical signature analysis, you get actually some statements also which are generalization statements with respect convergence in probability here. So if you somehow have, let's say, a semi-martingale which lies in the closure, or which lies in this set here, which I describe here, you can learn along one trajectory the coefficients, and then you know if you generalize for another trajectory, then you have in probability a result which is close to it, and you can make actually topologically relatively precise statements about this. Okay. This is semi-martingale signature, and let me now return to what I promised before, to a little bit of references for signature, and also to one problematic aspect about signature. So signature is used by the groups in Oxford and Berlin and at Imperial College in order to approximate path space functionals, and this has been successful and beautiful instance of provable machine learning. Just to mention Harald Oberhauser and Terry Lyons and Emmanuel Perez Arribas, Sina Nejat, they are working in different areas to approximate path space functionals by signature methods. This works very well and has one bottleneck, which is actually interesting to analyze. And the bottleneck is that signature is a high-dimensional object. High-dimensional, infinite-dimensional, potentially infinite-dimensional object. And it is therefore, depending on the grid on which the signal U is given, can be very complicated to calculate or cumbersome to calculate. When you think how many components signature has, like say you have a two-dimensional control, and you would like to go for order of accuracy M100, then you actually have to calculate 2 to the power 100. So a really large amount calculations in order to get all iterated integrals. That is problematic and can cause problems. Second, signature is a polynomial object and therefore comes with all problems of polynomial regression. So this might not be very well conditioned, and therefore calculating those regressions, evaluating those regressions might be problematic. And third, we have here in this lecture the point of view of reservoir computing. Therefore, we are expecting reservoirs, also when they are constructed mathematically, to have analytic tractability and have random features. Signature does, in a way, not have both. It is first an infinite dimensional object and therefore has an infinite complexity to be calculated. And second, it does not really have random features. Not that it is necessary to have them, but we know that there are very important instances of reservoir computing where actually these random features are present, and these are successful instances. In that sense, the question is there an approximation of signature which has random features and which does a similar job to signature and which is an analytically tractable object which you can relatively easily calculate? And this is actually the goal of the last part of today's lecture. This introduces first this famous Johnson-Lindenstrauss lemma, and then I use this random projection technique in order to compress the information of signature into a lower dimensional replica of it. Let me here stop the sharing and use the time for a question, but if there is none, I just... Is there a question, Julia?
No, there are no questions.
Very good. Johnson-Lindenstrauss, one of the beautiful examples of a mathematical theorem which made a career. This is the paper, also typewriter, as the lecture notes of Paul-André Meyer and many of the papers from the 70s and 80s. And you see the title of the paper is very innocent: Extensions of Lipschitz Mappings into a Hilbert Space. And this was 84. Actually, as I usually like to say, when a paper is really good, it's not important that it is published in a very good journal. It can also be published in some journal. It can even be published in conference proceedings. It doesn't matter. People will anyway read because it's a good paper. It does not mean that papers which are published in very good journals are not good papers, but it is always something which I tell to my students, that the fight to get your paper in a very good journal is, if it is a really good paper, it's not necessary. Just publish it somewhere and don't waste time, because people will anyway read it. So this is one of the anyway read papers. I think these are conference proceedings where it was published, and this is the following statement. If you look a little bit down here, where is it formulated? No, sorry, I'm sorry, I went too far. It is here precisely. So this is this. Can you read that, Julia? One can see nicely.
Yes, yes, yes. And then there will be a questions, but
yes. So there is a certain lemma set. You have a set A, and you have a mapping from A into a lower dimensional space whose dimension somehow goes logarithmically with the number of points in A. This is n, and the mapping satisfies that actually such an inequality holds, and the inequality just means that the distances of points in A under this map F are distorted by a factor which is in percentage just tau, and tau is a number chosen at the beginning. So this means you can take a point cloud in a high dimensional space and embed it into a point cloud in a considerably lower dimensional space, such that the distances don't change dramatically. So it's an almost isometric embedding of a high dimensional point cloud into a lower dimensional space. The funny thing of the theorem is, of course, the logarithm here, because you know logarithm makes out of a large number actually a really very small number. So when you read this theorem backwards, it says if you have a k-dimensional space, you find exponential k e to the power k, let's say almost orthogonal vectors in a k-dimensional space. Because orthogonality, you can imagine, you can express nicely also by distances. And if you take here orthogonal vectors and the distances don't change dramatically, then the vectors remain orthogonal, even though it's a very low dimensional space. This is not what you tell your kids when they go to sleep, how a high dimensional space look like, because you always think if you have orthogonality, you need more dimensions in order to express it. But you have almost orthogonality in a high dimensional space. This can actually be also expressed in a low dimensional space. So this statement, which is here formulated innocently in this paper by William Johnson and Johnson-Lindenstrauss, I repeat it on my slides, we use in order to compress information. What was the question?
The question was by Nino, and he asked if this lemma can be applied if the object, so the signature, can be infinite dimensional. So if we need some generalization of this lemma in this case.
You will see how I apply it. Actually, this is a very good question. There are two ways how to apply it. First way is you discretize signature in time, and then you get finitely many points on the signature curve, or you cut the dimension of the algebra and truncate the algebra, then you get a curve in a finite dimensional space, and you can then use generalizations of Johnson-Lindenstrauss to curves in finite dimensional spaces. So there are two ways how to see that. So let me repeat the statement. You have an n-point set Q, and you find the dimension, which you can actually cook down to this number. It is the next integer to 24 times the logarithm of the number of points divided by 3 epsilon square minus 2 epsilon to the power 3. And epsilon was this accuracy tau in their paper. And then you find the linear map, actually, which restricted to Q has the property that lengths or distances don't change dramatically up to epsilon, a factor up to epsilon. And the interesting thing is the theorem is not only an existence statement of such a map, it's actually a construction statement. You can construct those maps actually as random matrices with a certain type of randomness. So you have to tune a little bit the parameters, but essentially these are random matrices who with a high probability satisfy the property that this holds. And actually, when you look at it from that point of view, you see this is just a concentration of measure result, where we know, of course, in high dimensions, Gaussian measures or other measures concentrate very much around their expectation. Okay, so we take this statement and we take such a Johnson-Lindenstrauss map, let's say, on cut off truncated algebra, and we take M, truncation of the algebra, we construct the Johnson-Lindenstrauss map there by just choosing such a map. We do not even specify a set Q, and we look at the following controlled differential equation, which has a constant time-dependent term which depends on signature, and which has a term which is a vector field, a linear vector field, which is the following. Z is in the low dimensional space, take the adjoint of the Johnson-Lindenstrauss map, this embedded into the high dimensional algebra, multiply it from the right with EI, and then project it back and divide by the dimension of the high dimensional algebra. So this actually will be a very large number, but necessary due to the properties of this guy here. And when you look at this dynamics, you can actually prove the following statement, that the dynamics of this equation is close in the following sense to signature if you take regression coefficients W and you apply them on signature. and you take the difference with the same regression coefficients applied to the solution of this equation, which I call a randomized signature, and the same regression coefficients composed with this random map, but still this is just a regression. So you have a regression of signature, you have another regression on randomized signature, then the difference can be estimated by the following term. You have something on the initial values, which has to be, you can choose by choosing the initial value of y0 appropriately, which you can choose actually 0, plus something which depends on a constant, which depends on the total variation, times epsilon, this is the number coming with the Johnson-Lindenstrauss map, times these two norms. Yeah. Q is now a set which you actually can choose. And when you think about this equation, you can take the best Q which you have here. You can take the infimum of all Qs because the left-hand side does not depend on all Qs. So you can choose Q optimally in order to make it as small as possible. What is this Q norm? The Q norm is a natural norm which you have with this Johnson-Lindenstrauss lemma. It's a sort of L1. You would say if Q is an orthonormal basis in a Hilbert space, the Q norm would be an L1 norm with respect to the coefficients. So now in the audience for the numerical analysts, all the alarm clocks should ring. If you have an L1 norm and W is an L2 vector and the dimension of the space is very high, actually this number will be super high. So there might be here a trouble. And in order to deal with the trouble, which was also troubling the authors of this theorem, Juan Pablo, Ludmila, Krista, Lucas, and myself for a long time, we need a second bit of information. The question is, can we actually choose the W sparse? Is there a possibility to choose that so that the L1 norm is also small, or this Q norm is small? And here I just introduced this little statement which is known to any computer scientist, but also to everybody in functional analysis or in convex geometry. This is this Morey statement. If you have a convex hull, a closure of a convex hull of a bounded set in a Hilbert space, the closure of a convex hull of a bounded set in a Hilbert space, then you can actually find convex combinations of m points of the set C, which approximate with accuracy 1 divided by m any point in the closure. And you can even say something about this constant. So this means also very sparse convex combinations exist in order to approximate with accuracy 1 over m, actually it's 1 over m squared. You see this is a Monte Carlo argument actually, with accuracy 1 over m, square root of m, not m squared, square root of m, you can approximate with a sparse convex combination any element in the closure of a convex hull. Yeah. So a probabilistic proof which goes with Monte Carlo, and this actually tells that if you have a representation of your dynamics with some vector W, which you can get out of regression or out of analytic theorem, actually you get also a sparse representation, and therefore you can choose this quantity here small, or not small, at least of order 1, not exploding. And in particular, not exploding with the dimension of the surrounding space of the large algebra. And in that sense, that's a good estimate. That's an estimate which shows that regressions on signature and regressions on random signature have a chance to be close. Good. That's the statement and the proof. So it's a combination of Johnson-Lindenstrauss on the one hand and Morey sparse convex combinations on the other hand. And the only thing one needs to know here is now how can we actually work with such a differential equation in order to get randomized signature actually calculated. And here it's actually relatively simple. By central limit theorems, martingale central limit theorems, you can say that this whole guy here is nothing else than a random matrix again. And this guy here appears to look like a random vector. So both completely forget the relatively explicit structure inside, because you somehow take signature, which is a very explicit object, you multiply it with random numbers and you sum up, what you get is a random number. And same here, you have this F star multiplied from the right with this generator, very explicit linear map. And again, F on it, what you get here is a random matrix. And therefore, the algorithm finally looks like following. And sorry, I made a little mistake here. There should be actually brackets. The algorithm looks as the following. If you take a random matrix AI applied to set and the random bias beta I, and you solve this differential equation, then this guy has almost the same expressibility properties like signature in classical rough path analysis, and therefore approximates well any dynamics y of a controlled ordinary differential equation, as we had it before. Beautiful is also, and I go here because I see my time is up, right, Julia?
Yes, please.
Yeah, you can do the same construction for randomized signature of semi-martingales, because this is a construction which actually does not depend on first order calculus, because everything is linear here. We have linear equations, and there it does not really matter which type of calculus we use. So you can also provide the randomized signature for the semi-martingale inputs. And this gives a very similar result, and which I don't write down here. Let me just show you maybe just for 2 other minutes, Julia, is that okay?
Yes, it's okay.
Thank you. So if you want to see some code related to the analysis I presented, just go to my web page. There is the teaching link, and under teaching you find machine learning in finance. Take the last link. This is, I think, spring. No, yeah, on the page you find the spring 2020 lecture notes. This is actually a joint project with Christa, sort of a joint lecture which we are giving on machine learning in finance, and lecture number 8 of the spring term 2020 contains actually the code, a little bit of code for this, for what I showed you here. I call it deep simulation because it allows actually to construct the simulation algorithm. So it is explained here, so what I was explaining in the lecture, but I show you following thing. So take here, the red curves are the U's, so these are 2 Brownian motions in this case. The green curves are solutions of a stochastic differential equation driven by the red curves with an unknown dynamics. I know the dynamics, but I don't use it in the further analysis. What I do use is I construct a reservoir. So I take the 2 red curves and I send them into my reservoir, and this reservoir I think has in this case dimension 100. Yeah. And then I make a regression on the reservoir of the green curves, and I look a little bit how good that is. Actually, it is quite good because the regression only takes information up to 2000. And you see this already, what here is afterwards, this is out of sample. So the regression has never seen those parts of the curve, but here it generalizes already very well into this direction. And now we take a completely new path and we look whether we can predict the dynamics along this new path, and you see actually it does quite well. Of course, this is anecdotal, and there are a couple of things which one has to check here from an econometric point of view, but this is probably the cheapest regression-based mimicking of a dynamics you have ever seen in this short period. And it was just a regression which I do on the reservoir, which could be easily calculated and which has been precisely calculated by the recipe which I showed you before. And of course, you can make out of this scenario generator when you look let's say on stock prices. Take Microsoft, Google, Facebook, Bank of America, Amazon, Apple. So these are 6 stocks. Calculate, decorrelate, and normalize the returns by just taking the realized covariance matrix. Then you get the market Brownian motions. In this case, a 6-dimensional object, and these are the 6 market Brownian motions. I mean, they are not. Yeah, approximately like a Brownian motion. Some of them even manage to get through an independence test when you look at the increments. So you have now market Brownian motions, the input, the output are those prices. Some of them are there's apparently a drift present, the other one, it's maybe a little bit questionable. You put everything into a reservoir as we did it before, and you make the regression. This is now real data. And you see, actually, I think here I do the regression up to 500, and the rest is just given the market Brownian motion, how good it would predict. And you see, this is very, very good. So this is also a nonlinear econometric model by regression gives you actually very good prediction properties given the market Brownian motion. Of course, in reality, you are not given the market Brownian motion, but you can simulate a Brownian motion, and you can then calculate conditional laws of future developments of your market in the real world measure, just with a simple regression technique, which is estimating here a nonlinear econometric model. Okay, with this, with the invitation to take a look on this Jupyter notebook, which I think runs with Python 3.6, no, 3.7 even, but it's Keras and TensorFlow less than 2. But I mean, it's very simple code. So in that sense, you can easily translate it to higher versions. And this now brings me to the end of my lecture. I just return once again to the last statements here, and then I just go to some references. Take a look at the web pages of Juan Pablo, of Krista, of Lucas, of Ludmila. There's of myself. You find some papers there related to this lecture. And on my web page, you find Krista's and my machine learning in finance notebooks and lecture notes. And it remains me to thank you for your attention. Thank you that you made it for such a long time. And I'm eager to answer your questions.
Yeah, thank you, Joseph. And there are 2 more questions. One is from Juan Pablo, and he asked, why did you have 1 over n in, sorry for the pronunciation, Mori? And the one that he knows goes with the 1 over square root of n.
It's the squared distance, Juan Pablo. You see? So this is precisely the one you know. This is a Monte Carlo statement.
Thanks, you said. And the question by Lyudmila is, so use the non-market Brownian motion. How would you go about without in the out of sample?
Say it again. I did not fully understand the...
How would you go about without the it, so without the Brownian motion, in the out of sample?
I mean, I generate the out of Brownian motion out of sample.
So maybe, do you hear me?
Yeah,
Yes.
which one?
Joseph, it's just about the, so you already said that you're taking, for example, the real data, you are computing, well, you're using the real data in order to get the market Brownian motion, right? So it's all in sample. So how would you, do you have an idea how one would do it in the out of sample when, for example, in the forecasting exercise, when you don't have it available?
I mean, there are two things. So you do in sample the estimation of the regression coefficient.
Exactly.
And then you are asked to simulate a Brownian motion with drift, which mimics as good as possible the market Brownian motion, because the market Brownian motion with regression is a Brownian motion with drift. So what you actually do is you take your best estimator for drift of the market Brownian motion, you estimate this drift, and then you generate artificially a Brownian motion with precisely this drift. And this is provably by what you can show, then estimator from the conditional law of the future development of this price process.
Mm-hmm. I see.
So it is just as if you were fitting gauge, and I mean, in gauge you have the drift outside of the noise. Yeah. But here you have it inside the noise, so you're not you're somehow having it inside, and it remains you to estimate that, which is not a disadvantage. Which is not a disadvantage to have it like that. Yeah.
I see. Thanks.
In that sense, you can simulate, given on an estimate of the market price of risk, how this is called in finance, you can simulate future conditional laws of the evolution of this price process.
Mm-hmm. Thanks.
Okay.
And there is another question by Boumediene. So have you tried this with the stochastic differential equations with bounded noise?
I mean, the proof works for all semi-martingale noises with continuous trajectories, what the proof I fully showed. So when you don't have jumps, if the noise, you mean that the increments are bounded, right? Not the noise itself, because Brownian motion is also, every trajectory is bounded, but the increments are actually, if you take them infinitesimally, they are, you have, it depends how you look at them, but you have an unbounded feature because it is Gaussian. You can do it with bounded noise. I would even say this is, that's not the point of view in that theory. You don't need bounded or unbounded in order to prove those results.
Okay. He say thanks.
Yeah, thank you. Other questions?
No, there are no more questions in the chat.
Very good. Thanks a lot. Thanks for listening. It was very... Yes.
Okay, there is one more question by Juan Pablo.
Absolutely.
Joseph, you hear me?
Yes, very good.
Look, we've had this conversation already, but nevertheless, let me pose the question, because you see, you had this the discussion on the relation, or how to present basically signatures using Hopf algebras, and well, when we talk about this paper that we have in discrete time, then well, there we always work with tensor algebras. So you see, what is the feature that would make Hopf algebras special, or with respect to the use of a tensor algebra? Because, for example, these features that you were talking about, how the product of elements in the algebra becomes something linear, is exactly what you have in tensor algebra when you just look at bilinear forms of vector spaces. Well, they become linear when you look at them as linear forms on the tensor product, right? So what is the operation here that would be missing if, instead of using in this construction algebras or free algebras or Hopf algebras, we would just use a tensor algebra?
I mean, the tensor algebra is somehow tailor-made for the first order calculus. If you have higher calculus, or if you have some second order object or higher objects, it is sometimes more natural to use other Hopf algebras. They have the same property of this product of linear functionals is a sum of linear functionals restricted to the group-like elements, but they have let's say, sometimes more sophisticated algebraic structure. But in principle, I would say you can formulate a lot of things already in the tensor algebra, and you don't, in our theory, you don't lose much by talking of the tensor algebra. You also see that, for instance, semi-martingale signature, even though it is a higher calculus, you can also formulate in the tensor algebra, and it does not hurt. But if you want, why they use it in branch draft path theory, there are sometimes very particular calculi which you have for a certain rough path, and then it is an advantage in order to write down things economically, to use other Hopf algebras. So it is rather, when you write then those expansions, you would like to write them somehow in a way which is minimal as possible. And this is not always possible by choosing tensor algebras. This is how I understand it.
Very good.
Yeah, so it is just, in higher calculi, you can write everything down with the jets, but sometimes those jets have additional algebraic relations, and then it's better to go to a special, by factorizing something out, and go to a special structure.
Okay.
Yeah, so this is what happens. They have names. They are Kohn-Kreimer algebras, which appear there, and Larson algebras. So they are used then in branch draft path theory. And also, when you look in the paper of Martin Heira in the Inventiones paper, you also find those algebras there as examples.
Thanks a lot, Joseph.
Thank you.
So we start the contributed session, and the first speaker is Boumediene, and he's going to speak about learning dynamical systems from data, a simple cross-validation perspective. Thank you.
Okay, thank you all for coming, and thanks for organizing this very nice meeting. So it comes at a timely point. So do you see my screen?
Yes.
Okay. All right. Yeah. Okay. So this is recent work about learning dynamical systems from data using kernel methods, and particularly using a recent version of kernel methods that allows to choose the kernel called the kernel flows. And this is joint work with Houman Ohadi from Caltech. Yeah, so the context of this is about combining tools from dynamical system theory and machine learning in view of developing a data-based qualitative theory of dynamical systems for analysis prediction of nonlinear systems and control. And the approach here is to construct reproducing kernel Hilbert space from measurements where the analysis becomes simpler. So the summary of the approach is that we assume that there is a mapping from Rn into a Hilbert space that maps the ambient variable x into Z. And H here is reproducing kernel Hilbert space. And the goal is to perform a simpler analysis in H. So in general, the analysis is linear, but it doesn't have to be linear. So then we perform the analysis in H, and then we come back to Rn. And the transformation phi is obtained from the kernel that defines the RKHS. So in general, it's not necessary to explicitly find phi. And in practice, we will use this mapping called canonical feature map. So k is a function of two variables. So here, the first variable will be x, and then the second variable will be the measurements. So we'll go from R little n to R capital N, which with n is larger than little n. Yeah, and the data are used to construct the Hilbert space where the computations become simpler. So what are these reproducing kernel Hilbert spaces? So they appeared in the 30s as an answer to the question, when is it possible to embed a metric space into a Hilbert space? And the answer is that if the metric satisfies certain conditions, it's possible to embed a metric space into a special kind of Hilbert spaces called reproducing kernel Hilbert spaces. And there have been a lot of work about reproducing kernel Hilbert spaces, particularly starting from the 50s through the work of Aaron John, and then later on by Schwarz and many others afterwards. So before anything else, I mean, these reproducing kernel Hilbert spaces, they are Hilbert spaces with two extra properties. The reproducing property that we see in here, which is the property I. And then the second property is that the closure of the span of K is the Hilbert space. So reproducing kernel Hilbert space is a Hilbert space with a reproducing kernel whose span is dense in H. So the RKHS, I mean, traditionally have been used a lot in approximation theory, where the goal is to learn to approximate an unknown function from random samples, and so the approach is to minimize this functional here, which is the little e, so which admits a closed expression, but in practice, I mean, we have a finite number of samples, and we don't know the probability distribution rho. So what we do is that we discretize this criterion, and then we end up having this discretized version of E, which is an empirical error. And then we regularize just to get better approximation in the sense that it helps for smoothing and generalization. So in learning theory, the minimization is taken over functions from hypothesis space, often taken to be a ball of RKHS HK associated to a kernel K. And the function fs that minimizes the empirical error is the sum of Cj Kx xj. And this can be written as the sum of Cj phi j of x. And this is what defines the canonical feature map or Aronson map. And as we see here, I mean, if it's a linear combination in the phi j's, I mean, that's one of the advantages of working in RKHS is that you can linearize in feature space. So you would get a linear expression in the variables phi j. And the Cj's themselves, they are obtained by solving a linear system, which is given by the following equation. And here in this context, learning is the process of approximating the unknown function f from random samples on Z. Another application is to probability measures in RKHS. So if we have an RKHS on a separable metric space X with a continuous feature map phi, so if we define the kernel mean embedding of a probability measure P as the mean in the RKHS. So you have the probability measure P, and then you map it into RKHS, and then you compute the expectation, and then you get what is called the kernel mean embedding. And the maximum mean discrepancy is an integral property metric that is defined as the distance between two kernel mean embeddings of P. So we'll have the MMD between two property measures P and Q is the norm in the RKHS of mu Kp. So the kernel mean embedding of P minus the kernel mean embedding of Q. So this constitutes a measure of heterogeneity in between measures. Yeah. Okay. So now we want to just see how this kind of frameworks helps to learn dynamical systems. So we are going to focus on toy models and then see how we can apply this to analyzing time series. So one of the questions that remains to be asked here is how do we choose the kernel, and this is where kernel flaws come in. So the problem that we have here is just to come back to the problem of approximating an unknown function from random samples. So given an input-output data x1, y1 to xn, yn, we want to recover an unknown function u star so that u star xi is equal to yi. So in the setting, so this is, as we saw, is the problem. The problem is ill-posed, but in the setting of optimal recovery, this problem can be turned into a well-posed problem by restricting candidates for you to belong to a Banach space, be endowed with norm that is defined in a non-trivial way, but it's well defined. And then identifying the problem of optimal recovery as the minimizer of the relative error, which is the following one. So we have u, which is the function that we are trying to approximate, and v is the approximant. And then by considering this min-max problem, one could turn the ill-posed problem into well-posed one. So the method of kernel flaws is based on the premise that the kernel is good if there is no significant loss in accuracy in the prediction error if the number of data points is halved. And so this led to the introduction of this relative error rho, which is the norm of v star minus vs squared divided by v star square. So this is the relative error between v star, which is the optimal recovery of u star, which is the unknown function, based on the full data set, and then vs is the optimal recovery based on half of the data set. So here half is just a number, because we explored later on that it could be just any random number between 0 and 1. So half it just doesn't really matter. So in that setting, so the vs, the approximant, admits this closed expression, and then this is what we are going to use for predictions in case of chaotic time series. So we also so that would be the algorithm. So you take you have some samples. So first, we considered like a random subsample of the original sample, and then at each iteration we define the rho, the relative error, and then we evolve theta, which are the parameters of the kernel, by considering gradient descent in the direction of direction of rho. So we have a parameterized kernel. For example, you have a Gaussian, and then you want to find the variance, or you have any other kernel like so like the polynomial kernel, and then you want to find the power of the kernel. So so you define the relative error, and then you run stochastic gradient descent to update the parameters of the kernel, and then you repeat, and then you will get some the algorithm converges. I mean, here what is lacking is really proofs of convergence, but while listening to Joseph's talk, it seems that there are some connections there. So that's why I was asking so many questions about it, because somehow it felt that there are some links that can help find some better foundations for this kind of algorithm. So in the case of dynamics, so we have time series in RD, and the goal is to forecast xn plus 1 given the observation x1 to xn. So we assume that the data are coming from the following dynamical systems, which is like some discrete time dynamics. And then we want to approximate f dagger. So we just going to use the same closed expression that we had before. that was given in the case of function approximation, but here we want to approximate dynamics. So yeah, so we use the same kind of expression. So we would get the following approximant, which is the one that is known in kernel methods, except that now we want to update the parameters of the kernel in such a way that we get better prediction results. So what we also did in this work is that we also updated so redefined the metric that allows to update the parameters in the dynamical context. So the first one is the one that was defined in the case of function approximation, which is like the row that is associated to RKHS norm. But then we introduced two other ones. The first one is the metric associated to Lyapunov exponents. And the premise that a kernel is good if the estimate of the Lyapunov exponent obtained from the kernel approximation of the dynamics does not change much if half of the data is used. So we introduced this rho L, which is the difference between two estimates. I mean, and then it worked also well for the toy models that we used. And the other one is a metric associated to the maximum mean discrepancy, where we update the parameters by considering gradient descent of the row MMD, which is you just take the MMD between two subsamples, and then we want to minimize the MMD between these two subsamples to update the parameters of the of the kernel. So that's these are so we use these three metrics for these toy models. So yeah, we use this kernel. So which is the combination of the triangular kernel, the Gaussian, Laplace kernel, the locally periodic, and the quadratic kernel. So here the unknowns are all these parameters: alpha 0, sigma 0, alpha 1, sigma 1, alpha 2, sigma 2. Yeah, alpha 3, sigma 4, sigma 5, and alpha 4. So we update we update the parameters of the kernel by this algorithm of kernel flows using these three different metrics, and then we applied them to the following toy models. And the first one is the Bernoulli map. So we generate time series from the true dynamics, and then we don't know the dynamics, but so we want to approximate it. So yeah, so we could see that for different initial conditions. So we get, in the case, the red is the case of the initial kernel, where we started with some random numbers. So you see the prediction is not that good, but by using the learned parameters, the prediction is good. And same for the one on the right. So you have the red is so the red is the approximation using the learned kernel. So here, yeah, the red and here on the left and the right are not the same. So they are referring to different things. So and then the green here is the one with the initial kernel, and then the blue is the true dynamic. Yeah, same for the Lorentz system. So here we also used the same kernel. So same thing here. So the true time series and the approximated ones, I mean, they seem to be very close to each other. And same, so these are the errors for different components and different norms. And yeah, and then also a nice thing is that also we are able to also have nice estimates of the long-term behavior. So here it's not only about being able to predict the short term, but in the case of Lorentz systems, so we could see that we are able to get good approximations of the attractor. So using a learned kernel, so here on the left versus the true versus the approximated versus the initial kernel on the right side. Yeah, so that's that's a short talk. So yeah, for other references, so there is like a lot other interaction between machine learning and dynamical system. You can watch a longer version of this talk on YouTube, and then you have other references about kernel methods for dynamical systems. Yeah. Yeah, all right. Yeah, thank you.
So thank you for the talk. And there is a question by Lyudmila.
Yes.
And she asked, one may be also interested in recovering all Lyapunov exponent and not only the top one.
Yeah, good question. Exactly. Yeah, yes.
Can you modify your row to account for that case?
Yeah, I think that is possible. You're right. I mean, here, like, it's just more of. I mean, I see kernel flaws mostly as a philosophy. So it's So if one wants to recover more than the top one and all of them, then you can modify definitely a row and then make sure that you have that you update the parameters of the kernel in such a way so you get like another row with all of them. Yeah, but that's a good question. Yeah, that's right. Yeah.
And maybe one more short one, if I'm allowed.
Yes.
So, Boumediene, thanks a lot for the talk. I have, maybe it's because of my ignorance, but where does this criterion come from where you don't want to lose the quality? Basically, looking at the half of the points. So where this half of the points is coming from, this is something standard in this kernel methods literature. This is an ad hoc criterion. Where is it coming from?
That's good. So, it's not coming actually from kernel methods. It's coming from optimal recovery. So in optimal recovery, they use this random subsampling. So the half is not really strict. It can be a random variable. Actually, I tried for each iteration a random variable between 0 and 1. So a random number, sorry, between 0 and 1. It works as well. Yeah. So. But it comes from optimal recovery. So I think, as far as I know, I mean, we are the first one who introduced this kind of techniques from optimal recovery to the context of learning kernels for dynamics. Yeah, but the half, I mean, the half is not really strict. I mean, it can be a random number, but sometimes, so sometimes it can be 0.25. Sometimes it can be 3/4, and then you would have to play. Actually, you could play with this number. Yeah.
Thanks a lot.
So are there any other questions? Yes, there is one question by Juan Pablo.
Boumediene, you hear me?
Yes.
Okay, hello, thanks for the talk. Look, very quickly, well, you have this representation of the dynamical system into the RKHS Hilbert space. Luke, is there anything that you can prove about the geometric properties of that? Do you have an embedding there? Ultimately, do you get topological conjugacy in the RKHS, or that's a difficult question, right? Yeah,
I think it's a difficult question. Yeah, so this is why when I saw your paper, actually, I mean, your recent paper, I think there may be like things to be explored there. Yeah, right. Especially if we could see the link, I mean, between reservoir computing kernel methods, there may be things that can be done in that direction. Yeah, but sometimes we don't have any clear understanding of the dynamics in the RKHS. But yeah, you are right. I mean, that's still an open problem. Yeah.
Thanks a lot.
Yeah, thank you.
So thank you again, Boumediene.
Yeah, thank you. Yeah, thanks.
And now there is another talk. Hi, Luigi.
Yes, good morning. I'm going to share my screen.
Yes.
So can you see the slides?
Yes.
Okay, so first of all, thanks for organizing this conference. And I worked at this paper with my two co-authors, Massimo Riccaboni and Armando Rungi. And we are all from the IMT School for Advanced Studies in Lucca. In this paper, we did a forecasting exercise for the US gross domestic product with a neural network ensemble. So I want to start this presentation by showing you this plot, where there is the US gross domestic product from 1970 to 2020. In the shaded gray area, you can see the NBR recession period, while the plotted red line is the mean of the process. So at a first glance of this graph, you can see that the mean slightly changes over time. But if you look a little bit more carefully, every time there is a recession period, the process of the GDP experience a drop in value. So we can say that somehow this variation in these dynamics in the trend is somehow driven by the recession and by the crisis happening in the economy. So in light of this, we want to propose an innovative tool to explain and predict the GDP. in particular to account for these trend dynamics during the crisis. So basically, from one side, we are going to use the benchmark model to now custom forecast the GDP. So, for instance, the dynamic factor model, integrating this technique with models from the machine learning side, in particular the recurring neural network. So for what concerns the previous studies, we have, as I said, from one side, the macroeconomic forecasting literature, so basically mostly Stock and Watson and Giannone et al. For nowcasting and forecasting GDP with dynamic factor model, which is based on an estimation with the principal component analysis. And then we are going to integrate with the neural network forecasting techniques. And we would like to include this paper into this new branch of literature, which is still ongoing, which is trying to forecast during times of crisis. So basically, we are going to test our model into a test set where there is the 2008-2009 crisis, and maybe for future works, if these tools works for sure, we are going to propose it for forecasting during the COVID crisis, which is still ongoing. So let's go back to the main goal of the paper, to the main picture of this work, which is to find a model able to account for such trend dynamics. But first of all, we need to select the right set of inputs to be fed into the model, because by definition, the gross domestic product is a kind of the mirror of all the economy. So basically, of all the economy and all the economic fluctuations in a country for a specific period of time. So in order to mimic all of the economic fluctuations in a country, we need a huge set of information. So how to get all this information? We are going to use monthly macroeconomic indicators to be fed into the model. So it's important to say that they are monthly, basically because as some of you may already know, the GDP, the gross domestic product, is measured officially quarterly. So basically, by using monthly frequency indicators, you are going to exploit a higher granularity so that you can get more information. And this is in line with the benchmark model of Giannone. And these indicators are going to cover all the economic dimensions. And here you can have a look at all the model's inputs. So we had variables from employment and salaries, production, sales, prices, but also financial predictors. And if you want to have a closer look at all the variables we use, you can go into the appendix of our paper. And for every variable, we provided the thread code because we had all these variables from the thread database, so they are online and publicly available. So let's talk now about the model. So how to account for the shifts in mean and such structural breaks in the trend of the process. We want to find a model which is able to do this. So from one side, we are going to use the dynamic factor model, but with a potential possibility to use a dynamics in the trend. So basically, we are going to augment this dynamic factor model with a score-driven specification for the mean of the GDP. And we are going to combine this model with a recurring neural network in an ensemble process. So, and here we propose this methodology. For the recurring neural network, we are going to use the long short-term memory and gated recurring unit. But now let's talk about the specification of the model. So for the DFM, which is from Giannone et al. 2008, I think it's very well explained by these two equations, equation 1 and 2, in which we have a panel of monthly variables, which depends on a constant mean and R unobserved factors. So basically, the thing is that the main idea of this model is that there is a huge economy, which is somehow explained by a small amount of factors. And these factors has its own autoregressive dynamics, which is specified as a stable VAR of order P. So the estimation is done with a two-stage approach. So with principal and component analysis, we estimate lambda in ST and the vector of factors, and the coefficients in the VAR equation are estimated via OLS. And then Kalman smoothing is used to re-estimate the factors. So basically, after the estimation, we can finally identify the GDP equation in equation 3. So we have the GDP, which is our dependent variable, which depends on the factors, but also on this time varying mean, which we decide to model with a generalized autoregressive score specification by Kriel et al. For what concerns the recurrent neural network, our intuition is that during this time of crisis, we have such a high complexity that cannot be really explained by some parametric models. So, for example, the time varying DFM. So we want to exploit the features of the neural networks, especially using them during the times of crisis and recession. So we are going to combine these macroeconomic indicators through a nonlinear structure of nodes and layers. And we are going to use particularly the recurrent neural network because we want to exploit and capture the feature of the GDP, which has some sort of memory dependency. So for every time step, GDP is generated as a nonlinear combination of inputs at time t and the previous, the output generated at the previous time step. And the hyperparameters, in particular number of epochs, nodes, and layers, are trained with the classical backpropagation algorithm. Now we can go into our empirical analysis. And first of all, I want to do again a brief comment about the data. So there is this main idea, and this is from Johnson et al., that we use this large panel of monitoring indicators in order to somehow mimic an economic system, and then doing the dimensionality reduction with principal component analysis for the dynamic factor model. While in order to train the neural networks, we are going to use also a subset of all the variables, which is chosen by a simple correlation analysis. And for what concerns the observation, we are going to divide the data set into the classical training and test set, which are approximately 70 and 30% of all the observations. So a brief comment about the generalized autoregressive score specification. In order to do the estimation that we do with maximum likelihood with numerical methods, we need to assume some sort of distribution, and we tried two different distributions for the moment, normal one and a t-student, which we believe should better account for outliers. So here we do an estimation using all the data set and estimating a score-driven normal DFM. And the yellow line is the plotted yellow line is the estimated mean, so our alpha hat, let's say. Here instead, we use the training set in order to find the optimal estimates for a normal DFM gas and a DFM-T gas. And then you can see in green and red the plotted fitted values from the estimation. And we are going to use the same parameters to forecast in our out-of-sample window. So this window is chosen on purpose because there is as you can see, the 2008-2009 crisis. And so we're going to use this window also for the recurrent neural network because we want to evaluate how the models are able, specifically in this period of recession. And as you can see here, the normal one works better because captured better this drop down, which is in absolute value more than 8% of the GDP. In fact, if we look at the in-sample and out-of-sample performance, we see with root mean squared error, root mean absolute error, we see that in-sample t-student works better than the normal one, but out-of-sample it's the opposite. So for sure, this is an ongoing work, so we are going to try different specification of the DFM gas also to understand if it's all correct also in the estimation part with the maximum likelihood. So we're going to try different specification and we are going to find the best model and we will compare this with the recurrent neural network. And we compare this with a weights computation analysis. So basically, we use this weight structure in order to compare different predictions. How do we compute this? We compute by computing a weights for every forecast at every observation. So basically, we're gonna evaluate these weights with the inverse of the mean squared error. And in order to enhance clarity and to make results as readable as possible, we're going to choose the best two models. So basically one model for the recurring neural network side and one model for the time varying DFM. And here you can have a look at the results, a 1 quarter ahead forecast, so +1 forecast, +1 horizon forecast. And you can see there is in this out of sample window, there is 2008-2009 crisis, but also in the green shaded area, there is the crisis for the debt in Europe, which is not a crisis for US, but still we believe that some implication on the first and second moment of the US GDP. And then we plotted the DFM gas weights. So basically the weights of the time varying DFM. And here we can see that for every crisis, they experience a local minima. And this basically means that every time there is a crisis, the whole forecast accuracy moves onto the recurrent neural network, which is in this case is an LSTM1. So basically during the times of crisis, a recurrent neural network overperform completely the time varying DFM. And in order to use both forecasts in the same out of sample window, in order to possibly enhance accuracy, we're going to use an ensemble model. And in order to make it operative, we need to change a little bit the way we construct weights. So basically, we are going to compute the weights for the next observation by using the mean squared error computed with all the observations before the I+1. So basically, this ensemble gains accuracy, is more accurate the more we go through the out of sample window. And we compute it with mean squared error and mean absolute error. And here you can see the results. So here the ensemble increase the performance for what concerns the root mean squared error. It has 2.24 against 2.36 and 2.31. And also with the mean absolute error, we experience this the fact that the ensemble is superior. Now the funny thing is that when we compute root mean squared error, the LSTM is better than the time varying gas. But with the root mean absolute error, it's the opposite. So in order to make clarity on this, we carried a Dibble-Mariano test, and we see that we cannot reject the null hypothesis. So basically, the forecast of the neural network and the time varying gas has basically the same accuracy according to this test. But also because the out of sample measures of accuracy are really similar between them. So but of course, for sure we have this, but we have also seen that during the crisis, the recurring neural network, at least during the crisis, they overperform the time varying gas. So we are heading to a conclusion of this work, and as we have seen, okay, the first thing is that the ensemble always make some sort of gains in the accuracy. So it seems that using an ensemble is better than using the model, just using the single models, basically. But also, most importantly, at least for us, is that during the crisis, the recurring neural network works better and overperform the time varying gas, the time varying DFM, which is basically the benchmark for macroeconomic forecasting. So why is that? In our opinion, is that because during recession, there is such a high complexity that a parametric model cannot capture. But most importantly, the thing is that during this crisis, we have some sort of structural change. So we are going to have most probably some sort of change into the data generating process of the GDP. And we are going to know about this change just after the crisis. So after the drop down, after the recovery, and also maybe we need to wait to see other observations after this in order to estimate the new model and try to make inference about the new process, because you cannot make inference during the crisis. So basically, in order to improve the forecast accuracy, we need to use a model from machine learning which can exploit a higher level of complexity and can deal with the fact that we have this structural change during the crisis. So basically, the tool that we propose and that maybe we also want to test with future works in the COVID crisis, which we are experiencing now, is this ensemble with a time-varying dynamic factor model and a recurring neural network. So that's all for my side. Thank you for the attention. Here is my correspondence. If you have any doubts, just send me an email. And if you have questions now, please ask. So thank you.
So, thank you, Luigi. There is a question by Ludmilla and one by myself later.
Hello, you can hear me?
Yeah.
Yeah, so thanks for the talk. I have a very simple question. So when you're coming up with this, or maybe two very short ones. So the first one is when you're coming up with this average forecast, you're using the mean square errors in order to come up with weights. But as far as I could see from the dynamics that you're hunting for, right, in GDP, I mean, this is a usual thing that all you want to do is not basically undershoot in crisis periods, right? So what you want is to get the better forecast when things go wrong. So why wouldn't you go for some asymmetric losses which differ from, for example, mean square error or the absolute error, but for example, other consistent losses that, for example, are proposed in econometrics literature? So you have this Patton's paper on consistent losses which allow for consistent ranking between the models. So this could be something that you could, maybe that's not even a question, maybe a suggestion. And then one more is that I believe that you may hit on the same criticism as all of us are encountering, is that why would you come up with a mean forecast for neural network plus the score models? You could come up with 10 different models for modeling the GDP, and then you could come up with the average on those, estimating them on different time periods and coming up with a mean forecast. So, and obviously in that case, you will get a better forecast because we know that the mean forecast beats, right, the single models. So there are facts, you can actually prove that. So is there any answer you could suggest to that?
Yeah, well, so your question is related why I don't use, for example, 10 different predictions to build the ensemble, you mean?
Exactly.
Instead of doing just two. So basically, yeah, for sure, we thought about this, for example, using, a large set of predictions. We are also doing some tests in this direction, and we see that basically the more we increase basically the number of forecast and the higher will be the accuracy. So we are testing this, but we would like to focus more on this comparison between the, let's say, standard models like time-varying DFM and the recurring neural network. So also, as I said, to enhance the clarity of our work, because we are not that much into the ensemble model in the sense that we want to find the highest accuracy possible for the ensemble, but most importantly, we want to evaluate. And make this sort of comparison between neural network and standard models, especially during the crisis, because we believe that's the period where a higher complexity arises. So we want to focus more on this side. But for sure, it is true that by increasing the number of predictions, like in general, the accuracy of the forecast should increase as well.
Okay, thanks.
Okay, so I have only a curiosity. How do you initialize the ensemble learning algorithm? Because it seems that there is a big discrepancy in the picture that you show.
Yeah, you're right. The initial, you mean here, right?
Yeah, exactly. So
okay. Yeah. I initialized with, that's a good point. I initialized with 0.5 and 0.5. So basically, because I had to initialize because in the first plot that you see here, we compute, it is not a real ensemble in the sense that we just compute the weights. But for the first observation in the ensemble, one idea, you can also, instead of initializing in 0.5 and 0.5, we can use some in-sample information. So basically having a window which starts from the in-sample information and computing the mean squared error there. But I decided that I wanted to focus just on the out-of-sample performance of the two predictions. So basically, I was forced, to initialize to, and in this case, we initialized with 0.5 and 0.5. So by taking, the average.
So are there any other questions? It seems no. So thank you again for the talk.
Okay, thanks. Thanks for the conference.
And okay, the next talk is from Jeremy Turiel and Antonio Viola, that they present together, right?
Right, here we are.
And the title of the talk is Deep Learning Modeling of the Limit Order Book, and they make a comparative perspective.
Exactly. Okay. Can you see my screen?
Yes.
Okay. Good morning, everyone. We are Antonio Briola and Jeremy Turiel, and today we present our latest paper titled Deep Learning Modeling of the Limit Order Book, a Comparative Perspective, which is available on arXiv on SSRN and is currently under review. This work was fully developed at the Financial Computing and Analytics Center at the University College London, of which Jeremy and I are both members. The idea developed in this work regards the possibility to train deep learning models in order to approximate nonlinear mappings between historical limit order book states and mid-to-mid returns. But why deep learning for limit order book forecasting? There are three main aspects to be considered. First of all, the spreading of electronic trading has significantly increased the amount of data recorded during each trading day. This allows to feed and tune deep learning models, which are by definition data-hungry models. The second aspect regards the possibility to exploit the theoretical evidence according to which artificial neural networks are universal approximators, and making them deep increases their capability to learn complex relations and patterns from data. This means that at least from a theoretical perspective, they could approximate any mechanism underlying the financial market dynamics, independently from its complexity. The third aspect is strictly linked to the second one and regards the possibility to automatically create synthetic nonlinear features to encode an increasing amount of information. Before going deeper with the analysis of the dataset and the methods used in this work, let me briefly introduce the main object on which all the work is based on. It is the limit order book. Its structure and its main components are visually reported in the current slide. The limit order book can be defined as a self-organizing complex process where a transaction price emerges from the interaction of a multitude of agents in the market. The limit order book summarizes a a set of a collection of intentions of buying or selling integer multiples of a base unit volume at a certain price. The set of all available prices is discrete with a basic unit step known as the tick size. The number of price levels, both on the bid and on the ask side, determine the market's, the so-called market's depth. Let's now analyze the dataset and the methods used in this work. High-quality data represent the cornerstone of the research described in this paper. All the experiments discussed here are based on data from the Lobster dataset, which provides a highly detailed even-by-even description of all microscale market activities for each stock listed on the Nasdaq exchange. The training dataset, in this case, consists of 82 trading days that are about 4 months of the intercorporation limit order book data. The training data, the test dataset consists, on the other hand, of 20 trading days that are exactly 1 month of the same stock limit order book data. Training data have been scaled using a min-max scaling algorithm, and the scaler is then applied on the test set. Target classes for the limit order book state at tick time t have been defined computing the return quantile after 10, 50, and 100 price changes, the so-called horizons. The features that are fed to the models represent prices and volumes within the first 10 levels of the order book, as already said, for each side, so both for the bid and for the ask side. Those are then mapped by the selected model to a 3-class system, to a 3-label system. This is composed, as you can see below in the slide, of the lower 25% quantile, the middle 2 quantiles, so essentially between 0.25 and 0.75, and the higher 75% and upwards quantile. Speaking about the methods, we can say that the literature models the limit order book through architectures based on the underlying assumption according to which the 2 dominant dimensions, the 2 dominant dynamics, are the temporal and spatial ones. In order to verify or reject such an hypothesis, we tested a couple of models which are all listed in the current slide. Within them, it is relevant to say that the LSTM module, long short-term memory module, encodes the temporal dimension by keeping trace of short and long-term memory dependencies in sequential data. The usage of the self-attention modules allow to handle the spatial dimension in a static manner, because we use a mask clearly. While performing convolutions, the spatial dynamics are handled in a more dynamic way, because different levels are convolved together. Now, Jeremy will discuss results obtained applying those models to the data.
Yeah, perfect. Thank you so much, Antonio. So thank you, everyone. Just moving on to results here. Essentially, just wanted to start from a brief overview of what the results look like. So what we see here is essentially 3 main metrics evaluating the performance of the results throughout 3 different horizons. So 10, 50, and 100 price changes ahead return classification. What we can see here is essentially we have color-coded the different models, and what we're trying to show is essentially a kind of layering out of the models as they increase in performance. So kind of starting with Horizon 10, what you can see is that the random model and the naive model, as we would expect, stay in the center. So they're expected to perform worse, which means our models actually learn something which is above random or naive. And then moving out, we see the shallow SDM and the logistic regression models, which are able to train and learn something, but they're not able to produce complex features and hence improve the performance all the way up to the more complex models. And then we move up and we have self-attentional STMs, CNN STMs, and MLPs. As Antonio was saying, self-attentional STMs and CNN STMs are able to encode the spatial dimension. And we can see similar performance here with the first horizon. What we then see for horizon 50 and 100 as we move out is that self-attentional STMs worsen their performance, essentially saying that the static embedding of the spatial dimension is enough for the short horizon, but when you move to longer horizon and you're trying to model the dynamics, you actually need a more dynamic type of embedding of the spatial dimension, which is given by the CNN STM, and in particular the CNN module within that. And then what we kind of start seeing here is that the CNN STM seems to be slightly outperforming the MLP model, although not on a statistically significant level for short horizons. And then the MLP starts distancing out the CNN STM. So essentially, what would seem as the more basic model from a configuration point of view actually starts pushing out as we move to further horizons, and we need more model stability. So we're just going to see in the next slide something more about that. So in this slide, what we see on the left-hand side is something that essentially builds upon the previous slide, where we have done a Bayesian clustering of the model's performances. We essentially define a rope, which is a confidence level within which two model performances out of sample are considered the same, and then outside of that, they're considered different. So essentially, we have clusters that intersect here. We can see that one cluster essentially has the random model, which then in certain parts comprises the logistic regression and the self-attentional STM. As we have said, logistic regression doesn't produce as complex metrics, and the self-attentional STM worsens its performance. The LSTM itself has its own cluster, which does include the more basic models. And then as we move down, we actually see the better and better performing models in their own cluster by themselves, which is the CNN STM and the MLP. We should notice here that the self-attentional STM is comprised in the same cluster, although it is way closer to the edge of the cluster. So it just fits essentially by the brink. So essentially, we see this good performance here of the CNN STM and the MLP. Now, if we look at the table on the right-hand side, what we're going to see is that we have the CNN STM and the MLP very close in performance. The CNN STM does worsen in performance slightly as we move forward, whilst the MLP actually strengthens it. So that might suggest something of a more solid embedding from the MLP's point of view, perhaps given by the simpler structural build-up. Then we have the self-attentional STM that, as we said, works at the beginning, and then as you move out, starts worsening its performance. We have the LSTM again. Logistic regression has good performance actually throughout horizons, but it's not able to push the performance up as it doesn't have essentially enough parameters. And then we have the random model, which is obviously classified as zero correlation as it's random, and it should be. So just kind of drawing out in writing our conclusions here. What we see from our conclusions is that the logistic regression, again, is solid throughout horizons, but lacks this ability to produce more complex features. Then we have the LSTM. It accounts for the temporal dimension alone, so it does basically doesn't allow it to outperform the logistic regression strongly, and it has a decrease in predictive power for longer horizons. Then comes self-attentional STMs, which start looking at the spatial dimension. They start outperforming and they align with the state-of-the-art models, at least for the shorter term horizons. And then as we move on, we have the two main state-of-the-art models, which are CNN STMs and large MLPs, essentially. CNN STMs, as we said, yield state-of-the-art performance by encoding the both spatial and temporal dimensions dynamically. They are similar somewhat to self-attentional STMs, but they show how the spatial dimension becomes dynamic as we move forward in time. On the other hand, we have MLPs. What MLPs are doing, essentially, they're able to perform similarly or outperform CNN STMs when given a sufficient number of parameters, hence supporting the hypothesis that given enough parameters, MLPs are a universal approximator. And then what's interesting here is that we would have assumed from CNN STMs outperforming everything else is that the real underlying dimensions, or the real dimensions to interpret the limit order book and its dynamics, would have been spatial and temporal. But actually, by the MLPs here outperforming them, performing similarly, we understand that they're plausible way, a good way of encoding those, of encoding the limit order book, but they're not necessarily the necessary one. We don't need to impose them. And this type of understanding of the limit order book can be replicated and potentially even outperformed by regular MLPs. So those structures are essentially a good interpretation of the dynamics, but they're not necessarily the necessary interpretation. And that's very important because it kind of has come out in literature, the fact that these type of models are emerging, and it seems that they're necessary, and hence those are the dimensions. Those dimensions can be a good approximation, but we would like to stress that from the results, they're not necessary dimensions. It could just be a matter of parameters, or it could be a matter of approximation in the function. Just then following up on research directions, so just kind of what we're following up with as works. So we've moved from return classification to regression. And we're looking into gathering some theoretical evidence of how regressions work in these type of in these type of frameworks, and then how do we extract some information about the behavior of markets, and when you have a model that is able to predict, how does predictability scale in these chaotic systems, and we give some industry-oriented advice. And then we are applying these models to deep reinforcement learning, essentially not to impose a strategy on the prediction, but to allow a deep reinforcement learning agent to figure that out and see if efficient markets are a thing, or if we can beat those markets, at least theoretically. And then we have also multi-agent modeling in HFT for market making, always based on deep reinforcement learning. So just wanted to point to the paper, as Antonio was saying, it's on arXiv and SSRN, and it's currently under review. And we want to thank the organizers of the conference for the opportunity to present our work. And again, there's a lot of work to be done, so we always welcome interactions and collaboration. And thank you everyone for listening.
So thank you a lot for the presentations. And there are two questions that are actually entangled. And the question is if you use event time rather than physical time, because of the characteristic of the LSTM.
Yes.
So we spaced time series basically.
Yes, so that's a very interesting point. It's something that we had been discussing. Essentially, we haven't. So in this work, so in the work that we're working on currently, so the follow-up work, we are using real time, so seconds. In this work, we actually used times in terms of returns, so price, so the number of price changes essentially. You count not in tick time, but essentially number of price changes. What this essentially allows you to do is to adjust for price volatility. Essentially, if you try to build up quantiles, when you don't control for this, you end up with a lot of zeros. So you need to base either you take a very long time, or you adjust yourself for price volatility at the beginning, at the end of the day, and all these kind of adjustments that need to be taken, seasonalities. And essentially, one of the simple ways to do that is just to train the model on forecasting a number of price changes ahead. And then if you potentially test it or put it into production, it still gives essentially a directional prediction. And then you obviously have to figure out, based on the current volatility, what the prediction means in terms of time. So yes, we kind of avoided the time issue by doing this, but it's still a feasible approach. But yes, we're looking into time now. And obviously this connects to LSTM because LSTMs kind of need those discrete time steps, but also they need to assume something of an evenly spaced time step idea. And the idea of having price changes would essentially allow to discount volatility and hence assume that those fixed time steps are there. Otherwise, if you have varying volatility, it's as if you had way more or way less time steps at some different times. So I don't know if it answers the question, but maybe.
So is it okay, the answer for Fabrizio and Ivonni? Yes.
Okay. Cool.
So thank you again for your presentations.
Thank you so much. Thank you.
Thank you so much.
Second, there is another question. Okay, where do you train, by Matteo, where do you train a transformer net with granularity of seconds? Do you use a cloud?
So in terms of computing power, I assume you're talking about. So yeah, we essentially we have at UCL we have the opportunity to have quite a few GPU computing services. So essentially we have a university cluster. It does take quite a long time. So actually to train this, we use something like 6 months of training data. If you actually predict at each tick, essentially, and use this type of horizon, you end up with something in the order of 1 to 2 weeks of training. So it is a very computationally heavy thing, especially if you want to try and encode something as complex and have big enough models that actually are able to capture that complexity, but also not overfit those models. So be able to train it with enough data. You need something in the order of the tens of epochs on this amount of data with these large models. So essentially it's within the weeks, yes, like 1 or 2 weeks, yeah. So yeah, it's a lot of compute. That's definitely the point.
Thanks for the answer.
Thank you.
And I think we can move to the last talk of the contributed talk for today, and is by Daniele Di Sarli, and he's going to speak about efficient learning in recurrent neural networks.
I'll try to share the slides. Okay, so hello, I am Daniele Di Sarli. I'm a PhD student at University of Pisa. And indeed, I'd like to discuss about efficient learning in recurrent neural networks. In particular, well, we know recurrent neural networks in a nutshell. They are described by an equation which has a time dependency and describes the state of the network at a given time step. And this is a non-linearity which depends on the input x at a time step t and on the state at the previous time step. And these values, these vectors, are there parameterized by these two matrices V and W. And then from a given state, you can produce a prediction by using another parameter matrix U. And then the question becomes, how do you choose these parameters V, W, and U? And this, you can view it as a minimization problem. So it is a minimization between the actual output and the expected output. And since this is a minimization problem on a surface that is non-convex, what is typically done is to use gradient descent algorithm to optimize the function. So you compute the gradient of the loss with respect to every parameter, and then you take iteratively steps in the opposite direction of the gradient. This is the most widely used method for training recurrent neural networks. However, it also has some disadvantages, namely, well, there are a lot of parameters to update. So you have to update V, W, and U. But most importantly, this kind of method presents problem when there are long-term dependencies in the data. In particular, in this case, the training becomes difficult, slow to converge, and is typically referred to in the literature as the problem of gradient vanishing or explosion. Well, long-term dependencies happen when you have an output. Look at this example, which represents a recurrent neural network unfolded in time. Let's say that at time step t, your output is linked, it depends on the inputs that were provided to the network a lot of time steps ago. So in this case, when you optimize the function, when you optimize the network, when you compute the gradients of the error, the gradients must flow backwards in time through all these states. And what happens is that the updates that you perform to the parameters become very small. And then that's why it's called gradient vanishing, because since they are very small, it is very slow, the training process of the network. Okay, however, there are other approaches for recurrent neural networks. We have already talked today about acoustic networks and reservoir computing. what they really are, I'm going to provide a brief recap. They are just simply recurrent neural networks. In fact, the equation is still the same as before. It's identical as before, but they are studied as dynamical systems. So what happens is that you still have an input sequence which is projected by a matrix V into recurrent part of the model, which with a little change in terminology is called here a reservoir, which is a section of the model which is recurrent, but in this case is also untrained and very high dimensional typically. Then you take the state of this reservoir at a given time step, and you compute a prediction via linear layer, which we call readout. Now, the important thing about this model, the key characteristic of these echo-state networks, is that the only connections that you train are those in the parameters in the matrix U. So the only connections that are trained are these colored connections. All the rest of the parameters is fixed, is initialized and then kept fixed. This provides several advantages because, of course, if you only train these connections, then you can, well, your model is linear and you can use, for example, closed-form training algorithms to train your network. You do not have the problem of a gradient flowing back into the past. And of course, this is a very efficient approach because most of the connections are not trained, actually. However, to make this work, you have to meet some important properties of the reservoir. In particular, the reservoir must meet what is called the echo-state property, which states that a properly initialized reservoir will asymptotically wash out any information from the initial conditions. What this means more formally is that if you take a sequence of length n that we denote as Sn of x, and then you take any two states, two different starting points in the state space, if you apply the state transition function of the reservoir to the same sequence, but starting from these two different states, and you compute the distance between the resulting states after applying the whole the state transition function to the whole input sequence, this distance shrinks asymptotically and goes to 0 with increasing n. This is our key condition to make echo-state networks work, and a sufficient condition for meeting the echo-state property is the contractivity of the state transition function, which can be guaranteed if the norm of the recurrent matrix W is less than unit. Okay, this, however, can also cause some issues. For example, let's say you want to perform this simple task. You want to encode the number of tokens in the sequence that are equal to the first token. So we have two example sequences here. Here the first token is 0, and then a lot of ones follow. In the second sequence, the first token is 1, a lot of ones follow. So we would expect the resulting states after seeing these sequences to be quite different, right? Because we want them to end up in very different, because they have very different meanings. However, what happens if the reservoir meets the echo-state property is that you take, for example, H0 as the state after seeing the first token of the first sequence, H1 as the state after seeing the first token of the second sequence. And the more identical tokens the network sees, and the more the difference between these states shrinks until they become indistinguishable, basically. And that's not what we would expect, right? This happens because in this case, the information in the reservoir is laid out according to a suffix-based organization of the state space. And you can regulate the speed of this process of this shrink by, for example, increasing the dimensionality of the reservoir, so increasing the number of units, or choosing a different scalings of the matrices, but eventually some information will be lost. And if we want to, let's say, try and solve this problem, we can take inspiration from what happens in fully trained recurrent neural networks. So there is a popular remedy that is used for the issue of gradient vanishing that we talked about before, and it is of gated architectures. For example, if you take a gated recurrent unit, this is a recurrent neural network that includes some mechanisms, which in fact are called the gates. And this mechanism allows the state of the network, allows the network to control which information is remembered or forgotten from the state. So the network can dynamically decide which is the information that is important to retain in the state and what information is that can be discarded. And the behavior of these gates is learned by training via backpropagation through time. You train the whole network end-to-end by backpropagation through time and gradient descent. So this is the popular approach in the context of fully trained neural network. So one could ask this question: since we have seen that the architecture of a recurrent neural network is effective even if it is not trained, one could ask, are the architectural characteristics of a gated recurrent unit still effective when it is not trained? And we can test this. In fact, we did test this. We take the architecture of a gated recurrent unit and we treat it as a reservoir. So we...
Daniele?
Yeah?
Can you place the microphone a little bit better? Because so
yeah,
they say from the audience that...
can you hear me better now?
Yes.
Okay. So you can take the architecture of a gated recurrent unit, you can treat it as a reservoir. The matrices, then you take the matrices, you initialize them randomly, and then you keep them fixed. You choose a scaling based on hyperparameter search, and then you do not train them. We can use a task to test this, which involves long-term dependencies, which is what we want to test. So we can take a question classification task from natural language processing where sentences are represented as sequences of real-valued vectors. In this case, this is a classification problem. There are 6 classes, and the input is just a sentence written in English, represented as a sequence of vectors. Then what we found out is that there are improvements with respect to a simple acoustic network when you use a gated architecture, which is not trained. So you can see that this is the accuracy obtained on this task by an acoustic network. And the gated acoustic network, which is here, reaches better accuracy. However, this is not, simpler architectures can do better. So a leaky acoustic network, which is quite simpler, can do better. So there is some improvement, but it is not clear what it involves. However, there is another interesting fact. If you just treat the network, the main dynamics of the network as a reservoir, but you just trained the gates, you inject a training signal into the gates, and we represent this model as gated ESN RZ, you obtain a massive improvement in accuracy. So here, just the dynamics of the gates is trained, but the rest is still untrained. However, you can notice that while the networks where the recurrent part was completely untrained are extremely efficient, as soon as you start injecting a training signal via backpropagation and gradient descent, the training time rises a lot. And this is not what we want. So perhaps there are different architectures that are better suited for this, or there are different learning algorithms that are better suited for training just part of this network. So the point that I want to make is the architecture of a gated recurrent unit. Yeah, we know it is highly effective when it is trained, but we know it can be overkill for a lot of tasks where, for example, echo-state network work very well. However, this architecture is not necessarily appropriate for a completely untrained dynamics, as we have seen. The question is it even possible to completely avoid training the recurring connections? I mean, it is, of course, echo-state networks work fine on a lot of tasks, but when there are long-term dependencies in the data, maybe a dependency on the target of the task might be key for obtaining an organization of the state space, which is ideal, okay? And a way to have this target dependency is to have, the typical way is to have output feedback connections, but it is found that these are often ineffective in practical applications. So what we want is an interplay between reservoir computing techniques and learning of some reservoir connections. The way that we have tried of injecting a learning signal via backpropagation to time is currently too computationally expensive. This could be because of limitations in the way that commonly used frameworks work. It might be not. This is to investigate. However, it is possible that different approaches are more suited to this. For example, local learning algorithms like Hebbian learning, supervised Hebbian learning, could be very suited for training just the dynamics of the gates in such models and leaving the rest of the dynamics completely untrained. So this is a trade-off between efficiency and effectiveness in case of long-term dependencies. So if you want to read more about this, we have published a paper this year. It is named Gated Echo-State Networks, a Preliminary Study. And feel free to contact me or any other authors at the addresses that you see here. In case you have any question now, I'll be happy to answer it. Thank you.
So thank you, Daniele. Are there some questions or remarks? Okay, I have only a comment. If you have compared so far this mechanism with the so-called echo memory augmented network.
No, we do not. We did not compare it.
Okay, they're focused on this problem of the time dependency, and well, maybe I can send to you the reference.
Yeah, I'd be happy to. Thank you.
So it seems that there are no more questions. So thank you again for your presentations. And okay, we now have the break. So, okay, I would like to thank again Joseph and all the contributed talks, and we will come back at 3 p.m. and we see the talk by the lecture by Krista. And okay, have a good,
okay, maybe you can stop the recording.
Yes,
which I can't do because.
Okay, so welcome back to everybody. It is my pleasure to present Krista Cuchiero from the University of Vienna. And she will speak about from neural stochastic differential equation and signature method to affine and polynomial processes and back. So thank you, Krista, and have a good lecture.
Thank you very much, Julia, for the introduction, and thank you very much as well for organizing this workshop. So to all the organizers, Julia, Piero, Stefano, and Fabrizio, it's very nice that you organized this in spite of these difficult times, and I'm very happy to present here a lecture concerning neural stochastic differential equations, some signature methods, and the connection to affine and polynomial processes. So let me start with an introduction and some motivation and a question why modern machine learning technology has already quite successfully entered the world of dynamic stochastic modeling and in particular mathematical finance. And one answer that one can provide to this is that it enables realistic data-driven risk inference, and in particular financial risk inference. So why do I use the word inference and what is meant by this? So in fact, according to the Oxford English Dictionary, it is a conclusion that is reached on the basis of evidence and reasoning. And what is evidence and reasoning in our case? So evidence is everything that we get from data. So by this, I mean time series data, I mean derivatives price data, I mean macroeconomic data, so all kind of data that you can think of. And on the other hand, we still need to apply some reasoning, so we should not forget about first principle like no arbitrage in mathematical finance. We should be able to recognize universal structures from a statistical point of view, and we should in particular be able to use universal model classes. And the nice thing about modern machine learning is that it allows to conciliate both sides. So it allows to model as close as possible to high-dimensional data while we can still obey these theoretical principles, and in particular we have these universal model classes. And so what are the ingredients of machine learning that allow us to achieve this? And this is, so there are three parts that I want to present on these slides. And these are first randomly initialized or highly over-parameterized universal model classes. So we heard in the beautiful lecture of Joseph, we heard already what kind of randomly initialized model classes we can use. And so in particular, signature methods, random signature methods to approximate path functionals. But of course, it includes also artificial neural networks to approximate functions where, for instance, the space could also be infinite dimensionals. And in general, so these reservoir methods for dynamical systems. So these are examples of such randomly initialized or highly over-parameterized universal model classes, which make machine learning so successful. Besides these model classes, we always have to have an optimization criterion, which comes with a loss function or a certain metric. So for instance, I will present this later on, generative adversarial distances. So these can be the loss function that one would like to optimize in order to be able to fit the universal model that one started with to the data that one wants to fit actually. So this is the second ingredient. And the third one is an algorithm for training to finally find this optimum or to find an optimum in of this loss function to fit the data. And typically stochastic gradient type algorithms are used for that. Okay, so after this brief introduction, let me give an overview of the themes of this lecture that I would like to cover. So the first part concerns so-called neural stochastic differential equations, in particular the application in mathematical finance. So I want to introduce what I mean by data-driven generative modeling. Then I will say what is a neural SDE actually, and then I will show you how to apply this for calibration of particular models in finance, so-called local stochastic volatility models. And this is in fact allows us to solve an inverse problem with a perfect data match. And at the end, I will briefly mention also another application, which is also a similar model, but a little bit different, and they are called Schrödinger bridge-inspired models, which can be an alternative to these local stochastic volatility models. So this will be the first part. The second part will concern signature methods and so-called signature stochastic differential equations. So I will give you a review on signatures. So Joseph has already very well introduced that. I will recall some of the concepts so that we have the same notion how we will finally apply it to so-called signature stochastic differential equations. And then I will talk about expected signature for pricing and calibration. And this finally will lead to affine and polynomial processes, because one can have an affine and polynomial perspective to these signature and neural stochastic differential equations. So I will present first affine and polynomial processes in a very, very simple setting. And then we come to signature SDEs and view them as affine and polynomial processes. So this is then on the large space of this extended tensor algebra, where we consider affine and polynomial processes. And finally, I will also mention this, how it looks then for neural SDEs with analytic activation functions. So this is to tell you what this lecture will be about. And now let me already start with the first part, namely neural stochastic differential equations, and in particular their application in mathematical finance. And this part is based mainly on a paper with Wahid Khoshravi and Joseph Teichmann, which is called Generative Adversarial Network Approach to Calibration of Local Stochastic Volatility Models. Okay, so let me first start with generative models in finance, data-driven generative models in finance. So they come in form of GANs, so generative adversarial networks, and so this is one example, in fact, but it can also be these signature or random signature models. And one goal of these generative models is to be able to generate, if you want, artificial markets. And the idea behind is that you start with some input law, some standard law on path space usually. So this you can think of the Wiener measure on path space. And then the goal is to achieve some output law, some target law that you deduce from data. So somehow the empirical measure, or you deduce it from market prices. And you would like to match this law, this target law that you observe on the market. And now, what is a generative model? A generative model is a model that you can view as a map, which is called G theta here. And that depends on parameters thetas. And this map is a transport from your input law to your target law. So you can view this target law. This should be the push forward under this map G theta of your input law, this PI here. Now the goal is to find parameters theta hat such that your transport of your initial input law gives you the law that you observe on the market. So this is the idea behind this generative model setup. And of course, as I said before, one needs some optimization goal. One needs some distance. You need to measure if you achieved, if you could well match your target law. And one method to do it is what we do classically for calibration, is a classical calibration functional. So what do we want to do? Classically, we have model prices that we compute under some model, and we have market prices. So these are prices of certain derivatives that we get from the market. And now we need to find these model prices. So this would be the expected value under the target measure. So under this push forward of this map G theta of the input law of our payoff C. So C stands for the option payoff. And here we would like to match these model prices to the market prices. And we measure this distance with some loss function L here. And additionally, we have some weights here because usually we would like to match implied volatility, and therefore we could, for instance, use Vega weights to match this better. And now this transport map G is parameterized by this theta, and the goal is to find this infimum over all these thetas such that this model price is computed with the expected value under this transported input law such that this matches the market prices. Okay, so this is the classical calibration functional. Now one can add a little bit an adversarial part and think of the fact that it is not so clear what kind of loss function one would like to minimize finally. So one can parameterize this loss function by parameters gamma and also the weights by parameters gammas, and then have a more robust calibration problem where one takes a sup here. So this would be this game between the generator and the adversary, so that there is this inf sup game that one knows also from GANs. And of course, you could use other distances. So this comes from the classical calibration that we often have to do in finance, but you could also take other distances, for instance, Wasserstein type distances, where you replace this above sum by an expression like this, where you take the supremum over model classes here. So this could, for instance, be Lipschitz functions. Then one has really the dual representation of the Wasserstein type distance, and or it could be again neural networks or option payoffs. So in general, one can have certain distance functions d gamma such that the game between the generator and the adversary becomes such an inf sup game, or the distance between, in fact, the transported input law and the target output law. Okay, so this was actually in the ingredients that they had at the beginning. This was the second part. So this was the optimization criterion, the distance function. Now the question is, the first part, so what kind of models do we use? So what kind of randomly initialized or highly over-parametricized universal models do we use? And this, in fact, in these setups, reduces to the question, how do we parameterize this transport map G? And as I already said, we deal with highly parametric or over-parameterized models. One reason for this is that we leave the class of classical models where we have 2 or 3 parameters, is that these highly parametric models allow for so-called implicit regularization. So there is a paper by Jakob Heiss, Josef Teichmann, and Hannah Wute who addresses this question of implicit regularization, which is a result of over-parameterized models. And another reason why we use this is that it is nowadays the goal to learn the model characteristics as a whole. So we do not only want to calibrate 3 parameters, but we really want to learn the characteristics of the model. And they are often function of the underlying stochastic process, which induces the input law. So in fact, we really want to learn functional characteristics. And when we want to learn these functional characteristics, we rely usually on universal approximation theorems. So, and there are different kind of universal approximation theorems that one can use. And so the classical one is that we can approximate functions, continuous functions with neural networks. And this, in fact, leads to the class of neural stochastic differential equations. So one parameterizes the drift and the diffusion as a neural network. And in the case of signature SDEs, which I will introduce later on as well, there one relies on an approximation theorem that allows to approximate functionals of the path via linear functions of the signature. So what Joseph was addressing already in his lecture. So this is the different universal approximation theorems behind. Okay. So here I cite some literature on generative modeling in finance. It's certainly not the complete list, but it started with some work by Kondratiev and Schwarz in 2019, which is called Market Generator. And then a lot of papers followed. So Wiese, Wood, Bühler, deep hedging, learning to simulate equity option markets, Henri Labadère, generative models for financial data, a work by Hans Bühler, Blanca Horvath, Perez Arribas, Terry Lyons and Wood, a data-driven market simulator for small data environments, Beatrice and Xu, where they use GANs via causal optimal transport. And one paper to which I will refer later on as well, this is by Gieratowicz, Sabate, Siska and Spruch and Zurich on robust pricing and hedging via neural SDEs. And another one, again by Imanol, Perez Arribas, Salvi and Spruch on these signature SDE models for quantitative finance. So this is, these are some references on this generative modeling in finance. But now let me come to the definition of a neural SDE. So this is a rather simple concept. If you're familiar with Itô stochastic differential equations, then it just means that you parameterize your drift mu and your volatility sigma by a neural network. So these usually they are just function of your of the state of your process and on time. And now you take this again to be a function of your state and of time, but a particular function, namely a neural network, parameterized by a lot of parameters coming with this concatenation of affine functions with nonlinear activation functions. So this is a neural SDE. So nothing particularly fancy, but it is universal in the sense that we can approximate with this neural network any kind of function for the drift and for the volatility. And therefore we have a lot of flexibility when we want to calibrate such models to real data. And of course, we are not restricted to SDEs here, so we could also think of SPDEs, and we then could parameterize this mu and this sigma as neural networks on some appropriate Hilbert and Banach space where the process X then would live. So how is this now, how is the connection with generative modeling that I introduced before? So in fact, the solution measure of this SDE here, which I denote by p theta to indicate the dependence on the parameters theta here. So this corresponds to the transport of the initial input law, pi, of the Wiener measure. So in fact, you can view this law of a solution of this SDE as the transport g theta of this pi. And pi is the Wiener measure, which comes with this Brownian motion here. And the goal is to choose the theta to match the target distribution. And the target distribution comes, for instance, from the market prices that we observe. So what is an advantage of this new class of models is that they are universal in the sense that classical models can be arbitrarily well approximated. They are able to account for high-dimensional data, so we have a lot of freedom with this theta, so we can really match whatever we want. And still, it is in the framework of classical stochastic differential equations where we have a well-known theory. So in particular, in mathematical finance, questions of arbitrage can be addressed and answered. So it allows us to apply all the classical theory as well, while enabling a lot of flexibility and universality. Disadvantages, of course, are that the parameters are no longer interpretable. So if you change your theta a little bit, or one of the components of your theta, it's not so easy to tell how, for instance, prices would change. And this also leads to the question of robustness of solutions. So there is the question, you can, for instance, calibrate such models to vanilla options. You get, depending on your initial parameters that you use in your neural network, you will get several solutions which perfectly match your vanilla options, but then it's still not clear how robust it is for exotic options, for instance.
Krista, can I
Yes.
stop? So there is a question by maybe related to this part by Lyudmila.
Yes.
So Lyudmila, if you want, you can also switch on the Microsoft and...
Yes, hello. Krista, sorry to distract you, but this is more related to the previous slide when you were showing over-parameterized models. So something that I guess is the reason why people use over-parameterized models is because they have better generalization properties, right?
Yes.
Versus, so there is this the sweet spot that is in classical machine learning models is actually takes place also in the second region when you pass this inductive threshold. But here, as far as I understand, you don't have the problem of overfitting, right? So if you are just going for either learning a solution or approximating a process, then the better you are doing that, the better you are off. So for example, when you learn the parameters, so where does the overfitting danger come? And in what sense here the generalization may be important?
So, I mean, I think we still have the problem of overfitting. So it depends to what you would like to fit. So I mean, if you have the option prices, I mean, so usually you have more parameters than options that you would fit in this situation. So then you perfectly match this, but still, so therefore you can have a problem of overfitting. What do you think that, I'm not so sure what you...
You see, I looked at how people are using these GANs for example, the analogous types of setting that you're looking at here. And I always had this impression, and maybe I already posed this question to you some time ago in one of the talks, is that, well, since in the calibration tasks, you are going for parameters. So let's say you have simulated exercise and you want just to match perfectly the parameters, then what kind of a generalization one would hunt for? Is it either that is with respect to a new coming data, but then the empirical also measure that you want to match will be a different one, or where does this robustness with respect to the data, robustness with...
So one aspect is that we would like to get nice functions that so that we have, I will give you an example, that we will have certain functions that will enter in our neural SDEs, and they should have a nice behavior. And so this then has better generalization properties.
I see.
So yeah,
I see.
maybe you will see in the course of the talk, and otherwise we can
okay.
Later,
thank you. Thank you.
Yeah, thank you for the question. So now let's go to the problem that we are considering here. So we have such a neural SDE model, and how do we determine now the parameters? So one possibility is to use market prices from, let's say, J European options with a certain pay of GJ here. And we would now like to determine the parameters of our models, which is this theta, in order to match these market prices. Of course, this is only one choice. One could also, and these models also qualify for that, use more data, not just only option prices, but also time series data. So these many parameters allow this kind of flexibility as well. So here, this is the goal. Now I only have this, so L is the loss function. This measures the distance between the model prices and the market prices. Here we have some weights. I do not consider the adversarial part here for simplicity, but just this one. Now, model prices are computed as expected values of our payoff, which can depend on the whole path here of our, so X, we suppose this is some pricing model. This payoff can be a path-dependent option. So we compute this kind of thing. And we would like to match the market prices that we have. And for future use, I will call this PJ of theta. So this difference between the payoff and the market price here. And now I can write this again with the notation that I had before. So this will be the model, the calibrated model. So this is the push forward of my transport map parameterized by theta of my input law. And here I want to price this payoff, this option with payoff GJ. And the market prices are nothing else than the expected value under the target law, if you want. Okay, so this is my my calibration functional, and the way I find the theta is I take this infimum over those theta. And one crucial thing here is that it is not a standard stochastic optimization problem. So this optimization task is not a standard stochastic optimization problem. What do I mean by standard stochastic optimization problem? I mean a problem of this type here. So where you have the expected value of a stochastic objective function Q, which depends on omega, of course, and on parameters theta like this, so that we have so we just want to take the infimum of the expected value of such a stochastic objective function. The problem is in the calibration problem that the expected value enters non-linearly, in fact, because we have a loss function L, which is a non-linear function, for instance, the square, and in this non-linear function, the expected value enters. In the standard stochastic optimization problem, the situation is nice because in this situation, we have that this empirical gradient here. So if we take 1 over n and the sum over this over the gradients with respect to theta of this Q of omega I theta, then this is an unbiased estimator of the gradient of the expected value of Q theta if you can interchange the expected value and the derivative at least. And in the case, what we have in this calibration problem where the expected value enters non-linearly, so I show you again, so we have L and then enters the expected value here. So this is a non-linear relationship, and therefore the the gradient, which we can compute like this now for when we take instead of the probability, the empirical probability, which translates to this sum here, then we would compute the gradient like this here. So we have L prime, we enter the empirical mean, and then we have the empirical mean of the gradients. Then this is a biased estimator of the one that we would actually like to have and which we would need in order to use stochastic gradient descent. And this bias, this can be quantified. And in fact, so if you compare the expected value of your empirical gradient with the true gradient, so this is what you have here on the left-hand side, then this can be estimated with 2 over n, and n is the number of samples that you take, times the variance of this Pj. So remember, this Pj was the payoff minus the market price, or also if you take the variance, it's just the payoff. And so the square root of the variance of this times the square root of the variance of the gradient. And so you see that this bias is controlled by the variance. And if you have a high variance, then this bias will be big, and then stochastic gradient descent methods are not likely to work well. So this theorem you can find, for instance, in the paper by Gijatovic, Sabate, Vitales, Siska, Spruch, and Zurich, where, I mean, this is the proof is not difficult to get this. It's more or less Cauchy-Schwarz inequality applied several times. And yeah, but it's important that you control this bias by the variance. And therefore, it is important to get to try to decrease the variance of this Pj. So this was again the option payoff minus the market price, or in particular, yeah, we would like to get a small variance for to reduce the variance of the expected value that we so of the random variable that we would like to compute, so the price of this payoff. And in order to achieve this, one can replace this Pj here, which was just the blue terms before, so this Gj minus pi j. One can add a stochastic integral here, which corresponds to a hedge of this payoff here. So we can introduce these hedging instruments. So the hedging instruments are this C theta, and here we have then a stochastic integral. And if we would have a perfect hedge, then we would get zero variance, of course. But I mean, this is in practice not possible, but just getting a rather good hedge means that we have a new random variable whose expected value is still the same, because the expected value of this red term is just 0, but the variance is much lower. And this is a crucial point here, that we get the much lower variance, and therefore we can then use the gradient that I just showed you before. And even the standard Black-Scholes hedge works quite well. So if you have a non-path dependent option, then you can use this standard Black-Scholes hedge to already get a quite good variance reduction. Okay, and in fact, I mean, I just wrote down these hedging strategies, but it's not so clear how you get them. So if you have a Black-Scholes hedge, and if you have a simple situation where you could apply this, then it's fine. But otherwise, you also need to learn this. So this, in fact, what you do is you can also parameterize your hedging strategies as a neural network. And then, as in the paper Deep Hedging by Hans Bühler, Lukas Gonon, Ben Wood, and Joseph Teichmann, you can parameterize these hedging strategies with neural networks and then optimize again some loss function. So where you now plug in this Q here. So this is this new, so this is, you plug this in a loss function U, and you take the minimum over delta. So the delta are now the parameters of your neural networks, which parameterize the hedging strategies. And you try to find now your hedging strategy parameterized as a neural network, such that you then in the other optimization get a small variance. And so you can iterate these two optimization procedures. So the one for the theta, so this was the one for the model where you would like to learn the parameters of your neural SDE, and the other one for the delta. And having this variance reduction is really crucial to make this calibration work. And instead of the calibration where you do the optimization over the theta, this here is a standard, as you can see, is a standard optimization problem. Okay. Now we applied this in order to calibrate local stochastic volatility models. So let me just introduce this class of models. So these are models where the asset price process or the stock price process is given by such an SDE, where you have a fixed stochastic variance process. So this is something that you think from an econometric point of view should be a good variance process. And then you add a function L here, which depends on time and the current price of your stock, such that the goal is you match market prices perfectly. And you play around with the L to do that. And this L is called leverage function, and W is a Brownian motion again. So I wrote this down in a one-dimensional setup, but this makes also sense in a multivariate setup where you have a whole vector of prices, where you can replace this by the diagonal matrix of the prices, and L to be matrix valued and V to be a stochastic covariance process, taking values in the cone of positive semi-definite matrices, and W is then a d-dimensional Brownian motion. But here I would like to focus rather on the one-dimensional case in order to explain the concepts. So this leverage function, as I said, is the crucial part to calibrate to implied volatility or to market prices. So usually we calibrate to implied volatility because this is a better metric to get what is important on the market. And in order to achieve this goal, one can express, in fact, how this leverage function has to look like. And in fact, it has to look like this, that you can write down the leverage function as the Dupier volatility. So this is the Dupier formula, Dupier's volatility, and you divide by the conditional expected value of Vt given your stock price. So this is a formula. The problem that it is a very implicit equation for L, since for the computation you need indeed this conditional expectation. And in fact, this leads then to a Mikin-Vlasov stochastic differential equation, because the law also of the process enters. So we have, in fact, rather an infinite dimensional model, because if you write this down then in your SDE, you see that the law of the process itself in terms of this conditional expectation enters here. And for this particular kind of McKean-Vlasov equation, it's not clear how, existence and uniqueness is not clear yet. So in some particular cases it has been treated, but in general it's still an open problem because it's a McKean-Vlasov equation where you do not have any kind of Lipschitz properties in an appropriate space of measures. So yeah, therefore it's a formula which tells you how this L should look like, but it's it's not clear if the SDE actually is exists and is unique. Nevertheless, in practice, this formula is also used for the following techniques to solve for the L. So there are Monte Carlo techniques based on particle systems to approximate this McKean-Vlasov SDE, in fact. So you use particle methods to for this McKean-Vlasov SDE, where you regularize this expected value here, and you use a kind of propagation of chaos result, which theoretically is not proved, but which works in practice in most of the cases. Other techniques are PDE techniques based on the nonlinear Fokker-Planck equation for this McKean-Vlasov equation, or inverse problem techniques. And here I cite several references. And I mean, in all these approaches, the Dupere volatility function plays a certain role. And what our approach was that we would like to circumvent this completely, because in order to get Dupere's volatility, you need to have an interpolation of the implied volatility surface to get this first. And then you would use for instance, the particle method in order to compute the L. So in rather doing any kind of interpolation, our goal is to learn this L directly. So this leverage function directly. And in fact, how do we do that? So we parameterize this L via a family of neural networks. So we call this Fi, and each Fi depends on weights theta I. And in the multivariate setup, or in the one-dimensional, just think of the one-dimensional, so the D is equal to 1 here. So when we have the theta fixed, then this is just a map from R to R. And we parameterize it like this, that it is, so this L is then 1 plus this function Fi, and the I indicates that the T variable is in a certain interval, and these capital T's here, capital Ti minus 1 and capital Ti, they correspond to the maturities that are available. So we have maturities on the markers for certain options, and between those maturities we keep this neural network constant, and from to the next maturity we take another neural network Fi. So this is the way how we parameterize this leverage function, and it's clear that this leads to a neural SDE. In fact, so we do not have a drift here, but we have a volatility function. This volatility function is given by this expression, where we have this form of the volatility, where we have here these neural networks. So the square root of this VT we still have, but yeah, so the neural networks enter with these FIs here. Okay, and then there was the first question is, of course, if we parameterize this like this, do we get existence of our SDE? So if we have our leverage function parameterized by these neural networks, and if we suppose that these neural networks are bounded and C1, so differentiable in S and also in theta, and yeah, sufficiently nice also that the derivatives are Lipschitz, then we can first of all prove that for any given stochastic variance process Vt, and if we fix this L, then there is a unique solution as theta hat, where this theta hat is already the optimized thing in ideally, then this is, so this SDE exists. And one can also compute the derivatives of theta, which is important for optimization, in fact, so that we can compute gradients with respect to theta in order to optimize. And as expected, one can apply a chain rule, but one has to make this rigorous. And yeah, we can compute the gradient of this asset price process of this local stochastic volatility model via this equation. So in fact, if you formally apply the chain rule to that, then you will see what comes out. And yeah, this you can solve by variation of constants, in fact, because you have, if you see here, you have the gradient of this S theta is appearing here and here. So you have this part with times this one would give you a linear SDE that you can solve, and then you apply variation variation of constants to the remaining part. Okay. So here I wrote down the precise algorithm, what we do in order to calibrate this local stochastic volatility with the model with this neural, also with these neural networks for the leverage function. And in fact, we do this iteratively. So we start with the first maturity and we match then the parameters theta to our market prices. So to get really this perfect implied volatility surface, then we fix these parameters, and then we continue and fix the parameters of the next neural network. So maybe I go quickly through this algorithm. So in fact, we have this, so this K is in fact for the gradient steps. So you start with some initial theta 0 and delta 0. So delta 0 is for the parameters of the hedging networks, and theta 0 is for the parameters of the neural networks for the leverage function. And then you start to do your gradient descent, and you start with some K, and then you update it, and you simulate now with the weights that you had. You simulate 400 to 2000 trajectories. So with this variance reduction, we achieve to have this low number of trajectories. We do this on a certain discretization grid up to the maturity to which we are calibrating, and we use the fixed networks before, and we would like to find the parameters of the new network that we are currently with, the one that corresponds to the maturity that we are optimizing. So this is the one that we calibrate to. And so then we compute the cost functional, so the distance to the market prices or to the implied volatility of the market, and we use the fixed hedging control variates. So there we have the fixed weights for the networks of the hedging control variates. Once we have done this update step for the theta, we do an update step for the hedging weights, and this we iterate, and finally this converges, and we get at the end then the parameters of the neural networks for the leverage function which we are interested in. Okay, and we applied this to a Saber model. So the underlying stochastic volatility was a Saber model, and so this is the volatility here. And we looked for a leverage function such that we can match market prices, and the market prices were in fact generated prices from a parametric local volatility model. So we made a real test, a statistical test with, I think, 150 samples to really see if this method works generally and not only on one specific day. And we have always 4 maturities from 0.15 up to 1. Each maturity has 20 strikes. And so we have 4 neural networks. Each of these 4 neural networks has 4 hidden layers with a certain dimension, 64. Here we have certain activation functions. And as a variance reduction here, because we were calibrating to call options, we used a simple Black-Scholes hedge. And here you can see the results. So you start, so here for the smallest maturity, we start with a saber, a smile, which is not at all accurate. And we would like to fit the blue line. So this is the implied volatility corresponding to the data. And after the calibration or this stochastic gradient descent algorithm that I presented, we achieve really a perfect fit, and this holds true for all the other maturities as well. Here you can see this implied volatility error, which is really small, and this, yeah, you see that this is is the same for all the other maturities as well. And in fact, this is not only one example where it worked, but it really works consistently for all the 150 smiles that we tried. And in fact, you can here see in this box plot, you can see for all the strikes and for all the for the first maturity, here I only plot the first maturity, you can see the errors. So the orange line is always the mean error, and the other ones are this some quantals that you can see. And this calibration error to implied volatility is really satisfying. So it is around 5 to 10 basis points, which is a very accurate result, which we could consistently achieve over all strikes and also over all maturities. And then we also compared with some methods that are competing. So in fact, we compared with peer-to-peer. So this means that we do not have any stochastic volatility process, and peer-to-peer simply means that you can accurately fit your market smile, which you can also see here in this picture. So the peer is this blue line, the market is the red line. So this is perfect. And then we compared with the particle methods, which was introduced by Henri Labadère and Julien Gouillon, which works very well and is very fast, but has certain problems in for stochastic volatility models where you have a very high volatility of volatility. And so there are 2 methods, the one by Henri Labadère and Julien Gouillon, which is called PHL here. And then there's an improvement of this method by Muguruza. And both have problems matching this market smile when you start with a stochastic volatility model. In fact, a 2-factor Bergomi model with a very high volatility of volatility, so 400%. And this was our test to see if we can still match the market starting from such a stochastic volatility model. So if you consider the Saber model from before, there you replace the Saber by this Bergomi model, you make a very high vol of vol, and then you still try to find the leverage function. So this is the goal here. And we could do that. So in our methods, this is the violet line here, this was much more accurate than the other ones. So in these high vol of vol regimes of the stochastic volatility model, our method can outperforms the particle methods in terms of accuracy. However, what we have to admit is that it is much longer, at least on the computers that we used, than the particle method. But in terms of accuracy, we got very satisfying results.
Krista?
Yes?
There is a question from the audience.
Yes.
And by Lorenzo is in the example of European vanilla options, other time series can be used in the calibrations. I think to the underlying price, for example.
Sorry, I did not fully get the question. Can I see?
Sorry.
Maybe, yeah. In the example of European.
Sorry.
No.
Hi, I'm Lorenzo.
Hi.
So in the example of the calibration of the stochastic equation,
yes.
You calibrate it in the price of vanilla options, right?
Yes. So in this example, in the same example, yes, but you could use any other as well.
Yeah, so I can use also, for example, I think to the underlying, also the underlying of the option, or for example, with other structural derivatives, other risk factors.
Yes. So so this is the nice thing about this calibration method, that it is not linked to vanilla options. So you could also take some path-dependent options. Since we do everything by Monte Carlo, you are not restricted to this. So what becomes more complicated is maybe finding the hedging control variates in this situation, because we could simply use Black-Scholes hedges in this situation. But the method itself can be used for other option payoffs as well. Is
okay,
this
thank you.
your question? Or?
Yeah, okay, thank you.
Yeah. Thank you for the question. Okay, so this was concerning a calibration method of neural SDEs when we apply this to local stochastic volatility models and have this form of the leverage function, which is parameterized as a neural network. And I only want to go to another beautiful class of models, which was recently introduced by Henri Labordère, which is also in line with the stochastic volatility models, but a bit different and has, in my opinion, very appealing features. So Henri Labordère introduced so-called Schrödinger bridge stochastic volatility models, which I abbreviate by SBSV here. And this could be used as an alternative to these local stochastic volatility models. And in fact, they are of this form. So you have still your asset price given as usual some kind of geometric Brownian motion where you have a volatility process alpha, and this stochastic volatility process is given by this equation here. And in fact, you have to think of this, you start out with a model where you have only the black terms and not the red terms. So this would be your model that you would think of from an econometric point of view. So you observe a time series, you would say, okay, I would like to model my volatility like this. And then you, on the other hand, would also like to match your options. And in order to do so, you introduce this lambda term. And this lambda term is then just you can think of it as a change of measure, because an change of measure, in fact, because when you introduce this additional drift term, this corresponds to an equivalent change of measure coming from your initial probability where you had only these black terms, and now you go to a risk neutral probability. And risk neutral it is in any case, because here you have this martingale part, but you could have something else as well here. Then you make a measure change, and you have here something which is related to the market price of volatility risk. And in this situation, instead of the leverage function, which you have in the local stochastic volatility models, you change the drift of your volatility process in order to match the marginals or the market data that you would like to do. And in my opinion, this has an advantage over local stochastic volatility models because there you multiply with this leverage function. This is not an equivalent change of measure, and you substantially change your original stochastic volatility process in the sense that you are not in the same equivalence class anymore. And in this class of models, you only add this drift term in the volatility process, and this is then an equivalent change of measure, and you do not lose all the nice properties that you wanted to have of your volatility process coming from time series. So you preserve everything that should stay the same, in fact. So in particular, the vol of vol and these kind of things. Okay, and for this class of models, there's an analytic solution to match the marginals of your price process. So if you have a continuum of strikes for a given maturity t, then you can infer from all your option prices that you have for this continuum of strikes, you can infer the marginal distribution of your asset price at time t. So assume that you have this continuum of strike, that you infer your marginal distribution, let's call it mu. And now the question is, how can you choose your drift term in this Schrödinger bridge model to match, so this is rather deep in the model. So the drift term is on the volatility, and you would like to match the mu, which corresponds to the marginal distribution of your asset price at time t. And here's the theorem by Henri Labaudet. So if you start with this stochastic, this Schrödinger bridge stochastic volatility model without lambda. So if I go back to this slide here, so we do not have the lambda here, but just start with this, and we would like to determine the lambda such that we match the marginal distribution mu. And for this, you have to solve a strictly concave optimization problem given like this here. So what you have to do, you take the supremum over L1 functions with respect to your marginal measure mu and over predictable admissible processes delta, so some hedging or rather investment strategy. And you have to find the supremum over this functional here. So in fact, where does this come from? The idea behind these models is that you do some entropy minimization. So you start from your measure P, which was the measure where you did not have the lambda in your process. And you would like to find a new measure which minimizes your entropy between this measure and this new measure, and this new measure should additionally have the property that its marginal is mu and that it is still a martingale measure for the price process. And this, in fact, what you see here is a dual formulation of this entropy minimization that I just told you, and as constraints for that you have a martingale measure, you get this part here, in fact. And here you have, this is in order to match your marginal distribution. And suppose this is finite, the sup over this, then you get a unique solution called f star and delta star. And then you have an explicit expression, or more or less explicit expression for this lambda term, which is given by this expression. So where in fact, the solution of this optimization problem enters, so this f star and this delta star. And in fact, it enters like this, that you have to compute a conditional expectation of this expression given S and alpha. Then you have to take a derivative with respect to alpha. You take your vol of vol here, and here you take the correlation between the Brownian motions. So this is the expression. And if you do that, then you get that your price process has under Q a marginal distribution mu. which I think is a very nice class of models, and it's also very appealing that you can solve this theoretically like this. The question is how you find then this lambda in practice. I mean, you have to do first this optimization, which in this for one marginal is rather explicit. So for instance, this delta is a semi-linear, is a solution of a semi-linear Burgers-like equation. And also the F star can be expressed quite well. But if you have more and more marginals, things get more complicated. So one method is to do again, start with the neural network for the lambda and do the same procedure that we did for the local stochastic volatility model. So this would be one possibility. And the theoretical result tells us that we should be able to find a solution. And another possibility is that one could parameterize in these optimization problems, the F and this delta also as neural networks, then solve this optimization problem via stochastic gradient descent methods, and then learn the conditional expectation. So this would be a more tailored approach to the solution or to the theoretical solution of this problem. And so one of these methods, so either direct calibration of lambda or learning this F star and this delta star and then the conditional expectation, is promising when we have more marginals and if we want to match also other marginal distributions. So one thing which is an open problem in mathematical finance is that you find models that can match at the same time the implied volatility of your S&P options and the implied volatility of your VIX options. And in fact, these models allow, at least for one marginal, to do this. And you have a similar theoretical result when you include the VIX options. So when you want to match the marginal distribution coming from the VIX, there you have a more complicated optimization problem, but it is still possible to solve. And yeah, if you want to do this now for a lot of maturities, then I think these methods that I presented for the local stochastic volatility models can also apply for these Schrödinger bridge inspired stochastic volatility models, and in particular to be able to jointly calibrate S&P and VIX options. And yeah, so we are working on this, and yeah, I hope that I can in the near future present concrete results. So the second part, as already introduced, is on signature methods and signature stochastic differential equations. So I will repeat a lot of things that Joseph was already mentioning, maybe from a slightly different point of view. Yeah, so you will see. So let me start with the notion of signature of a path that you learned already very well this morning. It goes back to Chen already in 57 and 77, and it plays a very prominent role in rough path theory, which was initiated by Terry Lyons. And there's a beautiful book by Peter Fritz and Martin Heirer where you can learn a lot about rough paths and also regularity structures. And in a nutshell, there are three key properties of signature, why it is important. So the first one is that the signature of a so-called geometric rough path, I will introduce it precisely afterwards, uniquely determines the path up to so-called tree-like equivalences. This is first property. The second one is that under certain conditions, the expected signature of a stochastic process determines its law. So under this situation, it can be considered like a moment generating function as we know it from normal random variables. And what is important for us also is that continuous path functionals can be approximated by linear functions of the time extended signature arbitrarily well. So this is also something that Joseph was already mentioning, and I refer to this also to a universal approximation theorem. Okay, so in order to introduce this formally, let me start by introducing the tensor algebra. So we consider here D. D is greater than 1, and we consider the n-fold tensor product of Rd, which is denoted like this here. And when we start with 0, this is simply R. So it is clear what it is meant by this. So if n is 2, then we have matrices, and yeah, you can imagine how this continues. And then we deal with the first object is the so-called extended tensor algebra, which is in fact a sequence, which I always denote by this bold A. And the elements in this sequence are elements in this n-fold tensor algebra. So the an, so the nth element here is an element in this n-fold tensor algebra. So A0 is just a number, A1 is a vector in Rd, then we have a matrix, and so on and so on. So these are these elements in this extended tensor algebra. And then one can also consider the truncated tensor algebra. So this goes up to order n here, and this just means that everything after greater than capital N here is 0. So you have this finite sequence of tensor. And then if you only take one parenthesis here, then this is meant to take the union of this truncated tensor algebra. So here you consider only finite sequences of tensors, whereas in this extended one, you have infinite sequences. And yeah, as already said, so the generic elements are these bold A's. So what do I introduce here? These are some multi-indices and basis elements. So this calligraphic ID is the set of multi-indices with entries from 1 to D, and IN means that one takes those multi-indices which have length n. And now, if we consider a basis of this n-fold tensor product, so take just the standard basis of Rd, and then you can consider these tensor products of the standard basis for multi-indices in this set of multi-indices of length n. And this one is then a basis of this space here, so of the n-fold tensor product of Rd. And the way how you can write then an element in this n-fold tensor product is you just take coefficients and you take your basis elements, which are these n-fold tensor products of this ei1 up to ein. And for this one, so this n-fold tensor product with this indices e1 up to en, I call this ei, and this I here is then a multi-index that corresponds to this one here. Okay, so this is a basis representation of an element there. So in this Rd tensor n. And then you can define, of course, a scalar product on these spaces where you multiply. So you have, if you have an and bn in this n-fold tensor product, then you take simply the coefficients in the basis representation and you multiply them together, and then you sum over all these indices here. And if you do this on this whole extended tensor algebra, then at least formally you can write down this as the sum of the scalar products that you have here. Okay, so it's this is the notation that I shall use. Now let me come to this shuffle product. So this is the product on this famous Hopf algebra. that Joseph was mentioning. So without referring to the Hopf algebra, I just introduced the product here, acting on multi-indices, and then we will consider what it means for linear functionals. So I have now two multi-indices, I and j, and just indices a and b that are of length 1. So I need that in order to introduce the shuffle product in a recursive manner. And in fact, it is introduced like this, that you, if you shuffle the index I with the empty set, so this is in fact the empty word. So this is, yeah, then this is commutative, and it gives you again the multi-index that you had before. And if you now add to your multi-index this index A, which is of length 1, and you shuffle it with your multi-index J where you added B, then you have this relationship here, in fact, yeah. And so when I write this I, comma R, this means that I just concatenate these two indices. So often this is introduced with words and letters. So then the A would be, a one letter, in fact, and here it is, yeah, it's a way how to shuffle letters in a word. And yeah, here I wrote down some examples where you can use just the definition that you have here, and you see what becomes the one shuffled with 2. So if you have only words of length 1, then you get this, the shuffle product gives you this one, and with a word of length 2, you get these expressions. And the last one is 1, 2 shuffled with 3 and 4. So this is, yeah, simply by applying the above rules, you find this, and it is, yeah, you can see it as the possibility to interleave two sets, two sets of indices. So all you add all the possibilities to interleave these multi-indices. Okay. So this is the shuffle product, and it plays an important role when we come then to the algebraic structure that we will have on linear functions on the signature. So now let me start by introducing the signature of a smooth path, for where we do not have any problem to define integration. So let's consider a smooth path, so a function from the interval 0t to Rd. And the signature is then a map from the interval 0t squared to the extended tensor algebra. So we have this ST, these instances in time, and we can define then the signature as this sequence where the elements take values in this n-fold tensors. So it starts with 1, and then this is a vector in Rd, the next one is a matrix, and so on. And in fact, the way how this is defined is via these iterated integrals here, and they are given like this here. So in for a smooth path, you can just define this as a Riemann integral. And yeah, and these elements here live in this n-fold tensor product. So this is the signature for a smooth path. And then, of course, you can also consider the truncated signature up to order n, which takes then values in the truncated sigma algebra, in the truncated tensor algebra. Okay, so this is the iterated integrals that appeared also in Joseph's lecture, but now for a smooth path. If I do not indicate the intervals st, then I just mean the signature up to time t, and I do not always write here the 0t, but often just write t here. Now, the thing is that we do not want to deal with smooth paths only, because in particular in mathematical finance, semi-martingales play a big role. And then one has to go beyond the smooth paths and has to introduce the notion of so-called geometric rough paths. And for this, so let P be in the interval, in the open intervals 2, 3. So this corresponds to the P variation of the path that one considers, in fact. And then one introduces geometric rough paths as follows. So these are, again, like in the signature notation, these are is truncated signature up to order 2, but introduced in fact as limits of truncated signatures of order 2 of smooth paths. So you start with your smooth path, you compute signature, you only consider the truncated one up to order 2, you take a sequence there, and this sequence should converge again to such an object in this truncated tensor algebra. And in fact, it should converge in a P variation distance, and this limit then gives you a geometric rough path. So this is, yeah, what you how you introduce geometric rough paths. So it is the limit in this P variation distance of the truncated signature of smooth paths. And in fact, so this works for P in the interval between 2 and 3. If you go to higher order, then you would need to take higher order signatures that should converge. But since we are dealing with semi-martingales, continuous semi-martingales, our P will be in this interval here. So it is for semi-martingales, the P is greater than 2. And the notion for this geometric path, how we abbreviate it, is with this G omega 0T RD. So this is G omega is the notation for this geometric rough path. And the important thing is this is this Lyons-Victoire extension theorem, that geometric rough paths can be uniquely extended to their signature. So this, again, this map that maps the interval 0t squared to the extended tensor algebra. And this unique extension is then the signature of the geometric rough path. Okay. So the important thing is why we introduced this. This is because continuous semi-martingales are geometric rough paths almost surely with P greater than 2. And one way how to see this is via iterated Stratonovich integrals. In fact, so using von Kai approximation, one can see that we have exactly this convergence of which I talked, and it leads then to a signature which corresponds to iterated Stratonovich integrals. And yeah, so this is the same definition as before, only that it now is not only for smooth paths, but in particular for continuous semi-martingales, where we use this Stratonovich integrals, which is indicated with this circle here. And yeah, this gives us our signature in the continuous semi-martingale case. And yeah, it is, as Joseph also mentioned several times, a first order calculus that comes in fact from this approximation by smooth path, which leads us to the Stratonovich integral. Okay. Of course, we can also talk about this coordinate signature. So in fact, if we have a certain multi-index, then we can consider these iterated integrals corresponding to this multi-index, and this gives us a number then, and this is then exactly the coefficient that one has to put in front of this basis element here. So this EI is this tensor product of the corresponding basis elements that correspond to this multi-index I, and you have these coefficients here, and here you have a basis representation of the signature. Okay, so just some examples. If you have a one-dimensional path of finite variation, then your iterated integrals are just given by these Taylor polynomials. So this is in the one-dimensional situation. If you have a semi-martingale and you use the Stratonowicz integral, you just get the same thing. So you get these polynomials, which also appear in the in a Taylor expansion. In higher dimensions, things get more involved. So if you have a path of T and Brownian motion, then you can compute. So the first ones are T and Brownian motion, and then if you go to order 2, then you get T squared half. So this is again like this here. Also BT squared half, but you also have these ones. And here you see that this depends on the whole path. And yeah, then you can continue. And now let me come back to the shuffle product that I introduced. So again, as a to repeat, so the one remarkable property of the signature is that the pointwise product of two linear functionals, which is always a quadratic functional, is still a linear functional when we restrict it to the space of signature. And this means that every polynomial on signature may be realized as a linear functional. And this is, in fact, due to this theorem here, which goes back to Ree from 58 already. So if you have two multi-indices, and if you consider a linear functional corresponding to this multi-index, so in fact, what you do here, you extract from your signature, which lives in this extended tangent algebra, you extract the component that corresponds to the index I here, and you do the same here, extracting the one that corresponds to J. Then if you multiply this together, this is equal to doing the shuffle product between these indices I and J that I showed you before, and then apply this, so the index that you get out of this, this linear functional, then this you apply again to the signature. So this is the way how this algebra works. So how the product of two linear functions on the extensive tangent algebra, how this product actually is defined. So so this is important, and this we will see afterwards as well when I will speak about affine processes. So this shuffle product will appear there again. And yeah, just to see how this looks like in practice, to see how this shuffle product appears in a very simple example. So if you consider Stratonowicz integration of a semi-martingale, or you could take a path of finite variation, you would have the same. So you have integration by parts, meaning that the product, so we have a semi-martingale consisting of two components, x1 and x2. So sorry, here should be the one should be up. So for the components 1 and 2. And here you have the product done by integration by parts, just gives you this. And now you can write the left-hand side as this linear functional, as the product of these linear functionals. And here what you see is in fact the tensor product of E1 and E2 extracted from the signature. This is simply integration of x1 against x2. And here we have integration, sorry, there's a typo, of x2 against x1. And this here then gives you this is exactly corresponding to the shuffle product, in fact, as I showed you before, how 1 and 2 lead to the shuffle product. Okay. Now, a last thing about signature is the uniqueness. So in fact, an important theorem by these guys here is that if you have a geometric rough path, then its signature over the interval 0t, so this here, uniquely determines your geometric rough path up to so-called tree-like equivalences. So I do not want to go into detail what tree-like equivalences means, but it just means that it is reducible to a constant path by certain operations. So for instance, reparametrizations lead to the same signature. So this is something that you would like to avoid. And yeah, so this is, you have to exclude this tree-like equivalent path, and then you have uniqueness, so that the signature uniquely determines your geometric path here. And in fact, this is why one often adds some part, namely if you have a linear functional L such that the map from T to this linear function of your geometric path is strictly monotone, then the signature uniquely determines your path. And therefore, one often works with this time extended path. So one adds always time, and then your signature uniquely determines it. And so finally, putting all this together, the shuffle product property and this uniqueness property gives you this universal approximation theorem for signature. Namely, if you have a compact subset of your geometric your set of geometric rough paths that are not tree-like equivalent, and if you consider now a function from this compact set to R, which is continuous with respect to the p variation norm on this geometric rough path, then for every epsilon, you find a linear functional L on the signature such that you have this uniform convergence, or that you get that this functional L is uniformly close to your function of your geometric rough path. So this is just a consequence of the Stone-Weierstrass theorem, because you have with the linear functions, you get a subspace of your continuous functions on your compact set here. So if you consider this here, this gives you a linear subspace. And because of this shuffle property, this is a sub-algebra. It contains non-zero constant function. It separates point because of this uniqueness theorem. And therefore, this algebra stands and you get the assertion. So, I mean, this uniqueness theorem is a very deep theorem. I mean, the shuffle property, this is well known since a long time, but I think this uniqueness theorem is only due, it dates back to 2016, and before it was only known for rough paths of finite variation. Okay, so this is this universal approximation result, and we rely on that when we introduce so-called signature SDEs. So similarly as for neural SDEs, where we relied on the universal approximation theorem for neural networks, we now rely on this theorem to say, okay, we can get very generic stochastic differential equation if we approximate functions of the whole path by linear functions of the signature. And this is the idea of the signature SDs, which are introduced here. So we have some state space of R d-1. We have a driving Brownian motion, which is d-1 dimensional. And we take now as a drift part, we take a linear function of the signature. So in fact, of the time extended signature. So this is this x hat here. And also the instantaneous variance, this is this bold A, is a linear function of the time extended signature. So more precisely, in fact, so this B takes element of the extended tensor algebra and maps it to RD-1, and each component is such a linear functional. So this BI is an element of the dual or even of this extended tensor algebra whenever it makes sense. And similar for the A, so the A is a matrix, so it has, so the A is a map from the extended tensor algebra to matrices, and the components of this map are given by linear functions. And if you choose this B and this A appropriately, this allows you to approximate any continuous path functional, as we have just seen in this universal approximation theorem. And this just means that we get really a very general class of diffusions whose coefficients can in principle depend on the whole path. I mean, we do not address here any questions of existence and uniqueness, but I mean, there are certainly examples of such SDEs where we have existence and uniqueness. And yeah, so we work now with this setup. And let me just mention a subclass of these signature SDEs, which was introduced by Imanol, Perez Arribas, Christopher Salvi, and Lukas Spruch. They were called SIG SDE models for quantitative finance. And there, so they are R-valued, but this is not, this is just for simplicity that they do it like this. The difference is there that you have a model which is driven by Brownian motion, and then you take a functional of the time extended signature of this driving Brownian motion. So this is a little less general than our setup, but it can be embedded in ours. So in fact, we can use the setup that I had before, and we use as we have two components, namely the W is the first component, and then we have a second component. This would be then this process here, and we can write it in the form that I had before, where yeah, you can identify the A's and the B's. So the B is anyhow 0, and here we have simply this matrix, and if you square this matrix, then you would get the corresponding A's. And so the first component of this SDE, of the SIG SDE, is the Brownian motion itself, and then we have here this linear function of the first component only. And so this one is only to put it in the form that I had before, but this B2 never enters. So it is just to say that this class of models is embedded in this more general form. Okay, why are these models interesting? Because so in finance, they are universal in the sense that we can really approximate, again, very general models that we are, or very classical models, and we can fit data, and in a way which is which actually only depends in a linear way on this signature. So in fact, this L here is a linear functional. So in this sense, it is simpler than maybe neural networks where the parameters enter in a nonlinear activation function and so on. Okay. Why is it interesting in terms of calibration and pricing? So for this, let me introduce first the probability space on which we consider certain payoffs. This is, in fact, was introduced in this paper by Terry Lyons, Sinan Nejat, and Imanol Perez-Arribas. So you have a probability space where you take, in fact, p-variation paths, you consider their time-extended signature, and you close this with respect to a p-variation norm. So this is the probability space they consider. It's not really important for our purposes here, but just to tell on which probability space we are working here. And we introduce a pricing measure. So on this probability space with the Borel sigma algebra, we'll also introduce a pricing measure Q. And then what they introduce is so-called signature payoffs. And these signature payoffs are just payoffs from this probability space that I just introduced. And they have the particular form that they are linear functionals of the time-extended signature. So these are nice payoffs where their pricing is particularly easy. And these kind of payoffs, for instance, include Asian forwards. So if you take a certain linear functional, which is of that form here, and you compute then this pairing here with the signature, then you will see that you get this expression here. And this corresponds to a payoff of an Asian option, of a forward. In fact, so if one wants to compute rather a call, an Asian call, then one has to approximate it. So this is what Josef was also mentioning in his lecture, the problem that one faces with polynomial approximation of, for instance, payoffs like a call or a put. That's, yeah, there you have all the kind of problems that one also encounters in one dimension, in fact. But nevertheless, so path-dependent options of that form fall into the class of signature payoffs, and their pricing is particularly simple because you just have to compute. I mean, it's, yeah, I say simple, but later on I will tell you how one can actually compute that. So what you have to do is you compute the expected signature, because this is linear in F, and therefore you can put it out of the expected value. So this is this kind of thing that you have to compute, and this makes these signature SDEs and together with signature payoffs attractive. And one other thing is, which is nice for calibration, is so when you calibrate such models, the parameters that you have are actually these linear functions that you have in the drift and in the volatility, which I call B and A. So this bold B and this bold A. And if you are able to express for different B and A, this by another process, by the signature of another process Y, for instance, Brownian motion, the driving Brownian motion, which is possible in this class of SDE models introduced by Lukas Spruch and Imanol and Christopher, then you just have you have a much simpler calibration task, because you compute once the expected signature of this Y, and then you have to calibrate these coefficients only. So this is what I wrote down here. If you want to calibrate this kind of models, you do this over B and A. You have your signature payoffs, if it is the one that you want to calibrate to. And then by using the fact that you can express your signature via another signature of an underlying process, which does not depend on this A and B, you have a quite simple task to do, namely to find the A and B such that this expression here is matching the market prices. Okay, so this is one advantage of these models. And so the crucial question, nevertheless, is how can we compute this expected signature? And when X is given by this SIG SDE model. So this is important for the for pricing purposes. And here an affine and polynomial process point of view might help, because actually it turns out that these SIG SDE models are affine models or and polynomial models, but they coincide, in fact, in this situation. Good. So now I come to the third part of my lecture, namely an affine and polynomial perspective to this signature and neural SDEs. Are there questions so far, or can I just?
No, there are no questions in the chat. So.
Okay. So this is based on ongoing joint work with Sarah Svaluto-Ferro and Joseph Teichmann, which are the working title is Universality of Affine and Polynomial Processes, and a second one which is on arXiv is Infinite Dimensional Polynomial Processes, which is joint work with Sarah. Okay, so what I want to tell you is how one can embed, in particular, the SIG SDE models in an affine and polynomial framework. But before I come to that, I want to speak about our motivation in general to consider affine and polynomial processes as some kind of universal model class. And the reason behind that is that it is really remarkable how many models fall into this class. And I think you are all familiar with the finite dimensional examples. So a Levy process, an Ornstein-Uhlenbeck process, the Feller diffusion, Wishart processes, Black-Scholes model, Wright-Fisher diffusion. These are all examples of affine and polynomial processes. You have also infinite dimensional examples, so all well-known measure-valued processes like the Dawson-Watanabe process, the Fleming-Vio process, the Markovian lifts of certain Volterra processes, Hilbert space-valued processes, so you can have many forward curve models, lifts of rough volatility models, so the rough Heston, rough Wishart, rough Bergomi. These are all examples of affine or polynomial processes, and as we found out, or which was probably well known already, is that the signature of Brownian motion is, for instance, a polynomial process, and this applies to much more general signatures, namely to the one of the signature SDE models, which I want to show you. And therefore, the question we ask ourselves is this a kind of universal model class, and how can we make this mathematically precise? And the question that I want to ask in this talk in particular is, can we embed neural and signature SDEs in this framework? And so one objective is to linearize certain classes of SDEs via these signature methods. So what we learned is when we go to this extended tensor algebra and we use this shuffle product, then everything becomes linear. So all kind of polynomials reduced to linear functions. And this is something that we like in affine processes. And therefore, this hints already to the fact that it will be possible to embed these SDEs in an affine framework. And yeah, in fact, the goal is to develop an affine and polynomial theory for prolongations of generic stochastic processes by adding all monomials, for instance, or iterated integrals. And this then should lead to power series expansions of the Fourier-Laplace transform, as we know it from affine processes, and also of expected value of other entire functions, in particular polynomials. So in fact, we would like to be able to compute with polynomial technology the expected signature, as I showed you before. So this is a crucial thing for these SIG SDE models, to be able to compute this expected signature and the idea will be to apply the technology that we know from finite dimensional polynomial processes to do so. And yeah, so, some related literature that I want to mention here where expansions of such characteristic functions or Fourier Laplace transforms are considered. So there is work by Elisa Alosh, Jim Getterell, and Rado Radojcic, and also Peter Fritz. They use different kind of expansions than we do. So they rely on something which is called Diamond's products. But it is related work in a certain sense. And there's also work by Patrick Bonnier and Harald Oberhauser, where they consider signature, cumulants, and ordered partitions and independence of stochastic processes. So this is also somehow related. Okay, so now let me speak of affine and polynomial processes to introduce them in the simplest setting that you can think of. And then after this very simple one-dimensional situation, I will go to the extended tensor algebra. So to have really a big step, but you will see that many things that we see in the one-dimensional setup can be easily translated to this much more involved setting of the extended tensor algebra. Okay, so in this simple setting, we have an Itô diffusion in one dimension on some state space, which is some interval. And this Itô diffusion is given by this expression where B is the drift, some continuous function, A is the instantaneous variance, also some continuous function. And when is this now an affine or polynomial process? So in fact, you consider a weak solution of this SDE, and this is then called a polynomial process if B is an affine function. So I just wrote it down with some coefficient, a constant B and another constant beta times X. And the instantaneous variance here, so this A is a quadratic function, also written out like this. This is the definition, the very simple definition of a polynomial process. You start with an Itô diffusion in one dimension, consider a weak solution, and then a polynomial process in this simple setting is just means B is affine and A is quadratic. And what is an affine process in this case? This is simple when A, so the instantaneous variance, is only affine instead of quadratic. So in this simple setup, all affine processes are polynomial, which is in general not true when you have jumps. Then you need to add certain moment conditions. So polynomial processes are, at least in this setup, a more general class than affine processes. Nevertheless, both classes appear rather narrow with this simple definition, and we cannot think of anything universal at that time. Nevertheless, they have certain remarkable properties, namely, why are they so popular, in fact, is that the marginal moments of a polynomial process can be computed by solving a system of linear ODEs. So if you want to compute the expected value of this xt to the power n, you solve a system of linear ODEs. And this is something that we would like to translate also to the signature. And the second one is for affine processes, there you can also compute exponential moments. And in fact, in this case, you can express it in terms of solution of certain Riccati ordinary differential equations. So this is the situation for affine processes. And I want to show you this from a dual stochastic process point of view, which is a little bit different than in the original papers by Duffy, Filipovic, and Schachermeier on affine processes, and our paper with Martin Keller-Ressler and Josef Teichmann, and also the one by Dami Filipovic and Martin Larsson. So these were the initial papers where this kind of processes have been introduced. So let me give you now my point of view on this, or our point of view on this computation of expected values via dual processes. So in fact, we have three different methods how to compute the expected value of a function of our process at time t. So for this, let us denote the infinitesimal generator of a diffusion that we had at the beginning by this A, and you all know this is a second order differential operator of this form. We have f prime times b of x, so the drift, and the second derivative of f times 1/2 and the instantaneous variance function. Now, how can we compute the expected value of f of xt? This is in fact a solution of the Kolmogorov backward equation, which comes with the second order differential operator. So we have to solve this Kolmogorov backward ODE. This is one way to do it. Another way is via duality methods. So to introduce this, you have an independent Markov process UT with some state space U, say, and this Markov process comes also with a generator. Let's call this B. And what we assume now is that we have a class of functions that acts on this product. So S times U, S is the state space of our process X, U is the state space of this other process. And this new process with its generator B should have the property that if we apply A to this class of functions and where we fix the U and see it as a function X, this should be the same as when we apply B to this class of function where X is fixed and see it as a function in U. So if we have this equality, then one can prove that modulo some technicalities, the expected value of this F, which depends now on xt for fixed U, is equal to the expected value of f, where we fix the u and plug in the ut. And in the situation of affine and polynomial processes, it will turn out that this thing here is particularly simple. So this u, in fact, will be deterministic processes, and therefore we can get rid of this expected value here. And this gives the nice representation of the expected value of this class of functions that we will consider in this affine and polynomial case. And then there is a third way how to compute expected values. This is by taking the Kolmogorov backward equation for the dual process, in fact. So we can, of course, also compute this expression here by solving the Kolmogorov backward equation with this dual operator, where we start with this VUX, which is this family FXU. We solve this Kolmogorov backward equation, and then by the relation that we have from this duality in point 2, we can also solve this expected value by solving that Kolmogorov backward equation for the dual process. So this is the third method, and all three, or in fact, these 2 and 3 will matter for affine and polynomial processes. Okay, so now why is this important for us, and why is it important for the, why is it particularly nice for affine and polynomial processes, is because the function families that we can consider are in the one case polynomials, and in the other case they are exponentials. And there are several nice properties, namely that these families are distribution determining. So in the case of polynomial processes under exponential moment conditions, and this then allows to conclude whenever the dual process exists, uniqueness of the primal process. So this has also this nice feature. Coming from this dual process point of view, one can often conclude uniqueness of the primal process when one has existence of the dual one. Okay, now let's apply this duality theory to the polynomial case first. So there I have to introduce some notation. We have polynomials up to degree k given by this set here. So simply polynomials with coefficients c given like this. And we denote the coefficients vector by this, we simply collect the coefficients here in this vector, and this x bar stands for 1x x to the power k. So simply the monomials here. And notation wise, we write the polynomial of x and c. So this corresponds to such a polynomial. We can write it with such a scalar product, and this is simply the polynomial. I also want to say that an alternative definition for polynomial processes is that the generator maps polynomials up to degree k to polynomials up to degree k or smaller. This is an alternative definition, and this will play a role now when I introduce this dual polynomial operator. So as I just had in the slide before, we now want to find a dual process, a dual operator. And our class of functions are these polynomials. In the case of the operator A, we consider is acting in the variable x, whereas now we look at an operator which acts on the coefficients here. So we consider this map here as a map in the coefficients, okay? And now we would like that the action of our generator on the polynomials for fixed c is the same as this dual operator when we fix the x and see it as a function in c. And since everything is linear here, we can, and in fact, since this A maps polynomials to polynomials, so this means when I apply this to this polynomial, I get another polynomial. The only thing that changes are the coefficients. And so I have here linear operator acting on the coefficients. And this is how it looks like. So in fact, I get the polynomial with new coefficients, and here I have this operator. This I denote by this LK. So I identify this dual operator with a linear map LK acting on the coefficients. And now, in fact, I can see this as a restriction of a transport operator. So this B, when it acts on C1 functions, can be written as my matrix LK applied to the coefficients, and here the first derivative of J. And then you see already that this operator here corresponds to the generator of a deterministic ODE, and in fact a linear ODE, which corresponds where the matrix in this linear ODE is this LK. And this is then simply the dual process. Okay, so in fact, when we apply now the duality method from before, we have then to solve this linear ODE. So this in fact gives us the dual process, and we get as a result the so-called moment formula for polynomial processes. So if we solve this linear ODE, which is the dual process, then we can compute expected values of polynomials like this, simply by the solution of this linear ODE. So before we had this dual moment formula, the dual representation of this expected value with the expected value where we plug into our function the process ut and fix the x. So what we do here, we fix the x, and dual process is the solution of this ODE. So it is deterministic, and therefore we do not need the expected value. So in fact, this formula will play also a very similar role for the expected signature. So it's important to look at it again and to see how you compute expected values of polynomials. So you take your dual operator, you take the matrix exponential, you apply it to your coefficients, and you pair it with your initial value where your process started from. And in fact, we will have a similar formula for the expected signature. And now let me come to the affine case as well. And so there we have another family of functions, namely instead of the polynomials, we have exponentials. And in fact, for simplicity, I will put in this drift part and in the in the instantaneous variance part, I will put the constants equal to 0. So we had affine functions, but I will only consider linear functions, because this gives me, yeah, it's easier to express it like this. And now, how does the dual affine operator look like? So I have exponential functions. I consider this in two variables. I have the exponential ux. I consider this now as a function in u. I fix the u here, and the action of the generator on the exponential u should be the same as the action of b applied to the exponential, where I fix the x. And in fact, when you do the calculation, you see that this b can be expressed as, so it has to be this generator applied to the exponential ux. And if you write down what this is, then you get a function r, which is just the quadratic polynomial in u, times x times the exponential ux. So this is your function r here that will also appear all the time. So this is a quadratic function in u. Good. And this, in fact, now you can see again what is written here is, you can guess that this b operator is the restriction of a transport operator applied to functions g. So again, a first order differential operator where we have ru times g prime of u, because if you take as exponential function, so if you take g, the exponential here, then you exactly get what is written here. So again, we have that this dual operator is of this is a first order differential operator, so it corresponds to a deterministic dual process, and the vector field for this deterministic dual process, which is just an ODE, is this RU, and you see that this is then this quadratic has this quadratic form, and therefore we get that the dual process is the solution of a Riccati differential equation. And in fact, if we apply everything that we learned so far, we get as first thing that we can express the expected value of our exponential uxt as this vtux. So now I apply the third method that I had before. So this was using the Kolmogorov backward equation for the dual process. So the dual process, the Kolmogorov backward equation, is simply this here. I just wrote it down before. I start with the exponential ux as initial value of this ODE. I solve this transport PDE. This gives me a solution for the expected value of my of the exponential of uxt, where xt is an affine process, applying the third method of the way of computing expected values. And the second method means I solve for the deterministic dual process, which means I solve this Riccati ODE, and then I get what is usually known for affine processes. I get that the expected value of my exponential uxt is the exponential of psi tu, and psi is the solution of this Riccati equations times x. So I have these two possibilities. Either I can express the expected value of exponentials of my affine process as a solution of a transport equation, of a transport PDE, or as a solution of Riccati ODE, the exponential of the Riccati ODE times x. So this is also related to the method of characteristics relating ordinary differential equations and PDEs of transport type. So now this was everything in a one-dimensional setting, rather simple to ease notation and technicalities. And now we go to affine processes on this extended tensor algebra. So let me just have a look on time. Yeah, okay. So in the last 20 minutes, I will try to convey the idea how to translate this and how to get in particular that these SIG SDE models are affine processes and polynomial processes. So now we want to have affine processes on this extended tensor algebra where we actually are interested in the subset, in this group-like elements, in this signature subset. And so for the moment, I just denoted by an abstract set this calligraphic S here. Moreover, we need to introduce a set S star. These are elements in the extended tensor algebra and its complexifications such that when we pair them together, so when we have the scalar product, which I introduced before on this tensor algebra, that this is finite for all x in the state space. And I also introduce a set U hat. So these are those U, again, in this complexification of this extended tensor algebra such that the exponentials here are bounded on S. Okay. And now we introduce an affine operator, an affine type, a linear operator of affine type, actually. And this we introduce as follows. We say there should exist a distribution determining subset of this U hat and the map R that goes from this subset U here to S star, so where this pairing is well defined, such that when I apply my operator to these exponentials, it is of this form, namely exponential ux times Ru paired with x. So this is exactly the same form as I had before in the one-dimensional case. So I translate the one-dimensional form of my generator to this setup. So I've defined a map R. For the moment, I do not specify how this map R should look like, but we will see how the form is actually afterwards. So this is now an affine type operator that should act on the family of these exponentials. And then I can also define an affine process on this tensor algebra space or on this extended tensor algebra, namely as a solution to a martingale problem for this operator. So I have a tensor algebra space valued process X. So again, denoted by this bold X, already indicating that we will speak about signature. It should start at some X0. It should have a CAD-like version of these pairings here. And the crucial thing for the martingale problem is that, when we plug in the process paired with dual elements U, we plug it into the exponentials here, and we subtract the integral with respect to the S of the generator applied to this here, or this operator applied to this exponential uxs. This should be a local martingale for all U in my set U that I had defined before. And if we have such an operator of affine type, and if we suppose that the martingale problem admits a unique solution, then we call this process an affine process. So this is the definition. And now with this definition on this huge space here, we get actually the same result that we have in the one-dimensional situation. The only thing is that we need to be a little bit careful about moment conditions, and this is written down here. So we have an S valued, so S is a subset of the extended tensor algebra. We have a process that takes values there, so an affine process according to the definition that I introduced before. Then we need some conditions here and some moment conditions to which I do not want to go into detail. And then the assertion is that we can compute the expected value of the exponential of this xt paired with some dual element u. So the exponential of this here via this expression on the right-hand side. And this here is again a solution to a transport equation. This transport equation is exactly as in the one-dimensional situation. We have the vector field Ru and the first derivative of this v here. And this gives us an expression for the expected value of a moment generating function or a characteristic function of our affine process on the extended tensor algebra. And if we have further conditions, namely in fact that we can solve the tensor algebra valued Riccati equations up to time t. So this is in this situation the Riccati equation. Then we can also express the expected value of our exponential, so this characteristic function or the moment generating function as the exponential of the solution of this Riccati equation paired with the initial value. Okay, so in a nutshell, the whole theory of affine processes can be translated to this tensor algebra valued affine processes if we strengthen the moment conditions, and this is not negligible. So in practice, one really has to see how strong these conditions are. But under these conditions, we get these results. So now I'm back to the SIG SDE model that I introduced before. So let us recall it. So we have an SDE in dimension d-1 driven by a Brownian motion of d-1. And we have a drift, which is these linear functions of the time extended signature, and also an instantaneous variance, which is again a linear function of this time extended signature of this x here. So I wrote it down again. And now the nice thing is that these SIG SDEs are formally affine processes. And how do you see that? So the signature process, so the x hat is the one from the time extended process that I had before, so from the SIG SDE model. And now we can write down the map R. So in fact, what we can do is we compute actually the signature of this process that I wrote down, and then you can see via Itô's formula actually how this R should look like. And this is the expression. And what you see here is that the shuffle product appears again. And this, if you look a little bit more in detail, there you have the u's and you have also the u squares. So you have again something quadratic in u, a little bit more complicated expressions here, where this A and the B characteristics of our SIG SDE appear. But other than that, it is a quadratic function in U, which is complicated in terms of these multi-indices and the basis elements that appear, but the structure is not very difficult. And this is the reason for that is that using this shuffle product, everything linearizes. So it is again this beauty of this of the fact that the linear functions, the linear functionals are in algebra, and this which can be expressed via this shuffle product. Okay, and in fact, when you write down this R, you can then simply by Itô's formula prove that this expression here where this L is given by the exponential time this RUX here, that this is a local martingale, and then we are back to the definition of our affine process. So formally, this works very well. We get affine characteristics, we get this R, everything is nice and fine. The only thing is that one needs to find a set U such that this R of U maps to this S star. So remember, this S star was the set where the U and the X are well defined. So the pairing between tensor algebra valued elements. So this is not so obvious when this works out. But then the signature process of our SIG SDE is an affine process taking value in this extended tensor algebra, and X therefore is a projection of an affine process. And I think this is a very nice result, that this very class, this very general class of processes can be embedded in this way in the class of affine processes. I mean, for the expressions with the characteristic function and or the moment generating function, this is a little bit more involved because one has to check all these moment conditions, and this might not be very easy. So for the moment, it gives us a formal a way to find expressions for the moment generating functions, but it's still to work out for generic classes when these moment generations, moment conditions apply. Good. And now finally to the polynomial technology. So in this framework, because everything linearizes due to the shuffle product, so all polynomials become linear functions, we do not have to distinguish between affine and polynomial processes anymore. This is also a nice feature when we have extended everything, that finally polynomials reduce to linear functions. But we can still apply the technology of polynomial processes. And for this now, I write down the dual operator in the polynomial sense, which is given by this here. So this is simply the drift part, actually. So it is actually the k that we had before. So the order in the polynomials is just 1 that we need here because we have this infinite dimensional object. And this is, so this dual polynomial operator applied to the basis coefficients EI here. So this is the multi-index I that gives rise to the linear functional that I would like to consider. So this is this operator. Now I can define the exponential with respect for this operator. So simply as the usual exponential as this power series. And if this is well defined, so I need to pair it with the initial value. If you remember the moment formula from before, the initial value of my signatures is simply 1 and then I have zeros. So I'm interested only on the very first component of this tensor algebra valued object. Nevertheless, this could be infinite, but supposing that this is finite, and if we have certain moment conditions again, then the expected signature of my SIG SDE model, where I extract here the i's component, is given as this exponential of this operator here applied to this EI. So this is the one which I would like to extract. And I pair it with the initial value, and the one of the signature is simply 1, 0, 0. So this is polynomial technology to compute expected values of the signature. Okay, I think I have still 5 minutes, so maybe I briefly go through this example only. If we apply this to Brownian motion, then this is the simplest case what one can consider. So we can apply this polynomial technology to the case of a d-dimensional Brownian motion to compute the expected signature of Brownian motion. So in this case, this L operator applied to this basis element is given by this form. So you can compute the generator, you can see how this looks like. And then you take the exponential of this, you find this formula. So this is the formula that I just gave you in the theorem before. This gives you then this expression. So the expected signature of Brownian, of the E's, so of the E's component of this Brownian signature is given by this expression. And here you have to see what this means exactly. So certain becomes 0. And if you see what this gives you, you will find out that the expected value of so now this is in the expansion of the signature, this would correspond to the element that is in the it corresponds to the n-fold tensor product. Formally summed up, this gives you this expression. And if you then go for the whole signature and formally sum everything up, you get this formula, which is a well-known formula, which resembles a lot the characteristic function or the moment generating function of a Gaussian. And in fact, this was just to see that you can use this polynomial technology to compute these expected signatures. And in this situation, it has been deduced also by other methods, but the polynomial technology works also to find this expression for the expected signature. And the methodology works for much more general processes than Brownian motion. So for these SIG-SDE models. But I wanted to say that this nice formula can, for instance, be recovered. Okay, and finally, to go back to neural SDEs. So now I would like to see how things look like in a one-dimensional situation again. So, I mean, let's consider neural SDEs in a one-dimensional situation. First, I would like to see how in a one-dimensional situation, what this corresponds to. So if I do not consider the time-extended signature, but just signature, then as we have seen before, the signature is just these Taylor polynomials. And therefore, I can write this expression simply as functions which correspond to power series. So I can relate this signature SDE now in the one-dimensional situation to coefficients which are simply analytic functions, which converge have a sufficiently big radius of convergence. And in fact, this setup then covers neural SDEs with analytic activation functions. And then in this precise situation, one can consider the theorems that we had before, write down conditions when we have all these moment conditions that I had before. So here this is written down again in a specific setup. When this holds true, we get the same PDE expressions and Riccati equations for the characteristic functions. The conditions are now tailored to the one-dimensional case. I do not want to go into detail here. Only here are some examples which go beyond the standard affine polynomial case. And here it is the polynomial situation that I showed you before for the expected signature is also written up here in a more explicit form for the one-dimensional situation where you have to deal with an infinite matrix. But you get the same exponential, the same formulas that you had before, but it's, you have to deal with the exponential of an infinite matrix. that you have to solve. And again, one has to deal with convergence radio in order to see when actually we have this, that the expected value of our polynomial is given as the solution of this linear ODE, again, in the coefficients and again with an initial value. Yes, and so what we are interested now is to determine really classes of analytic functions where we have convergence of this the solution of these linear equations, in fact, when we consider this power series. So this is the question: when does the semigroup map analytic functions to these analytic functions so that we have really convergence on the whole space? And yeah, here are some examples that that go beyond the standard affine and polynomial cases. And now let me come to the conclusion. So what I wanted to tell you is that these generic classes of SDEs can be proved to be at least formally affine by lifting them to the signature space where all polynomials get linear functions. You have seen that in this function R, which determines the generator of an affine process, the shuffle product appears, and this tells us that we can really lift those generic SDEs to get only linear characteristics. And this gives rise to find power series expansions for the Laplace transform via affine and polynomial technology, in particular to compute the expected signature of generic SIG SDEs via polynomial technology. And this is then helpful for pricing, hedging, and calibration through this expected signature. And finally, these arguments also apply to neural SDEs, because if we have analytic activation functions, they can also be embedded in this framework. And so with this, I would like to thank you very much for your attention, and I would be very happy to take an Aperol Spritz with you
yeah.
the power of Pisa, but I think we have to postpone this, but I hope that in summer it will be possible. And thank you very much again.
Thank you.
Thank you to you, Krista.
So I'm happy to take questions if there are any.
Yes, are there some questions? So maybe I have one question. I don't know if it's a good question, but how one can incorporate some regularization techniques in this framework of neural SDE? Well, for instance, the injection of some noise or...
Can you repeat it again? What
okay, it's my fault that how can one can incorporate or can see some regularization techniques, well, for instance, some noise injection and so on, or dropout techniques in the framework.
What do you mean by regularization techniques for which class, in fact?
For instance, for the neural SDE.
Yes, but what would you like to regularize,
or some, for instance, like the dropout technique?
I mean, this you can do by simply implementing it in, when you implement your neural SDE, then as you do it for neural networks, you can of course also do that in your SDE, that you use the dropout technique also there.
Okay.
So
okay, when implemented,
that you optimize over less parameters.
Okay.
Which is certainly, which makes a lot of sense to do this, I would say, because often you have far too much parameters, and then to drop out some of them is of course very sensible.
Okay, thank you. Are there some questions?
I have a small question. Sorry, let me figure out how to turn my camera on. First,
it's who is it, Anastasia?
Yeah.
Yes.
Hi.
Hi.
Nice to see you. It's been a long time. Actually, I have a question. So first of all, really great talk. I really liked it a lot on all the subjects. And I had one question. So this is, I guess, one thing I probably think about most these days. It's universal approximation. And I think it's pretty much all I think about these days.
What is, I did not hear it. Which kind of approximation?
Universal
Yes,
approximation.
Okay,
yeah. So actually, I was thinking about the neural SDEs since Vahid sometimes or often talks about it.
Yes.
Yeah. So my question is, in what is it known in what sense precisely they're universal? Like usually, it's yeah. Because it'd be interesting.
It's a good question to see it if they can also, that you can do it also on a space of stochastic dynamics. I mean, here the idea is just, it really only comes from approximating functions by neural networks. So it is just saying that, okay, I think the space of SDEs which are driven by Brownian motion, and where in front of you have some coefficients corresponding to continuous functions, and you approximate those continuous functions by neural networks, then yeah, you can approximate this class. But it certainly would be interesting to see if on a set of I don't know, diffusion processes, continuous semi-martingales, this is somehow dense. But,
okay, so it's also still open. Okay, cool. Because I started thinking about this question.
As far as I know, yeah.
Oh, this is good. Cool. Well, thanks a lot.
Thank you.
Hi, Krista. Can I ask you a question?
Yes, of course.
How are you doing?
Fine, and you?
Fine, fine, thanks.
Was that the question?
That was the question. Thank you. No, I'm just kidding. I actually had the same question than Anastasis. He stole my question. But then, a follow-up question is like when you approximate your coefficients with neural networks. So where are you doing that? Are you truncating the domain or something to have these bounded compact domains, or what is the approximation happening? And how are you thinking about it? Like, is in the functions are being approximated in a uniform sense, I guess, or in which sense? And where?
So you are thinking now that you would like to be in a compact set for your state space, or
I don't know, is that the case? Well, I guess in that case, you could prove it more easily, but is that what you do when you implement, or I don't know, when you approximate the coefficients with neural networks, where are you doing this exactly?
So usually, I mean, if you take the standard universal approximation theorem, then you would do it on, I don't know, the unique cube, and you would approximate it there. So, but you're of course right that if you want that your process lives in a certain state space, then you certainly, it's not so easy to do this with neural networks and to get all the conditions such that you have stochastic invariance. So I think this is certainly, if you want to live in that your process is, let's say, in a compact, then this is not easy. So these neural SDEs that can be, I rather think of non-compact state spaces and hope that still there is existence, and that that one doesn't get a problem with blow-ups. So this is not fully worked out yet, but it's a very, very good question.
Okay, thanks. Thank you, Christian. Very nice.
Thank you, Sergio.
Are there any other questions?
Okay.
No. So thank you again for the presentation.
Yeah, thank
The
you
nice
very
lecture.
much for organizing everything, and yeah, and thanks a lot to the audience to stay so long. And yeah, it was a great pleasure.
Stephanie, if you want to say.
Oh, well, thank you, Krista. Thank you, everybody. And I think it was a great day, and looking forward tomorrow.